Welcome to the Mastering Python, 2nd edition, authored by Daniel Arbuckle. A video course by Pact Publishing. I'm Greg Arnold, and I'll be the voiceover artist for this course. Daniel holds a doctorate in computer science from the University of Southern California, where he specialized in robotics and was a member of their nanotechnology lab. He now has 10 years behind him as a consultant, during which he has been using Python to help him in assortment of businesses, from clothing manufacturers to crowdsourcing platform. Python has been his primary development language since he was in high school. In this course, the goal is to help you move from being a Python newcomer to being able to use an assortment of advanced technique. Along with C, C++, and Java, Python is one of the languages that everybody needs to know well. So, let's get you there. In Section 1 of this course, we'll have a quick primer on the Python language's syntax and semantics. Section 2 is about getting the Python runtime installed and usable. The videos in Section 3 cover how to create a Python source code package. Section 4 is covering several of the best practices, including source code formatting rules and the use of tools such as version control in virtual environments. In Section 5, we'll create a complete text mode utility program. In Section 6, we'll learn how to improve the performance of CPU-bound programs in parallel processing. In Section 7, we'll learn how to improve the performance of I/O-bound programs using asynchronous I/O. In Section 8, we'll cover several different ways in which Python syntax or semantics can be controlled programmatically from within our own source code. Section 9 is about automated unit testing and test-driven development. In Section 10, we're going to talk about reactive programming and the RxPy framework. In Section 11, we're going to talk about creating microservices. Finally, in Section 12, we'll talk about linking Python code with system-level code written in C. As you can see, the course progresses roughly from entry-level to advanced, but for the most part, each section is independent of the others. Feel free to skip around to the things that you need to learn, or work through the course in order to get up to speed. Python is, in my humble opinion, the best all-around language out there, and it's a whole lot of fun too. Let's get to it. Hi, and welcome to the first part of our section on Python Primer. In this section, we're going to take a look at some of the basic syntax and semantics of Python. If you need to get up to speed on the language, this is where we'll do that. We will be covering the basic syntax of Python, its built-in data structures, functions, classes, its standard library, and the new things in Python 3.5. This video primarily provides a basic understanding of the Python language constructs. If you feel you already have a solid grasp on Python, feel free to skip ahead. Python is a member of the C family of languages, like C++ and Java. But Python is more of a distant cousin, as the designers of Python are quite happy to do things in a different way if it seems better. Still, if you're familiar with C or one of its descendant languages, you'll find Python relatively familiar. Let's get down to the nuts and bolts. A Python program is written as source code in one or more .py files and consists of statements and expressions. Both statements and expressions tell Python to do something. The difference is that expressions can be combined to form more complex expressions, while statements can be combined with expressions, but not with other statements. Python source code files are executed from top to bottom as soon as they're loaded. by the Python runtime, which means that for simple programs, we could just write a series of statements in a .py file and then tell Python to run them. In this example, the if and else parts are statements, or a single statement with two parts. If you prefer to think of it that way, everything else is an expression. For more complex programs, we need a more structured approach. Like most programming languages, Python lets us create functions and classes in order to organize our code. If you don't know what functions and classes are, you could think of functions as miniature programs that could be used as building blocks for larger programs, and classes as combinations of functions, and data to create new kinds of data. We'll start with a brief look at functions. Functions are created using a def statement, which is a statement using the def keyword as its identifying component. As I said before, Python executes the statements in a .py file starting from the top. When it executes a def statement, the result is to create a function. That means that code that runs before the def statement does not see the function because it doesn't exist yet. The part of the def line inside parentheses is called the parameter list. It's a list of internal names for data values that are given to the function as input. Outside the function, those values might have different names or no name at all, but inside they'll be stored in these variables. The indented block of code immediately after the def line is called the function body, and you could think of it as the source code of the function. The code inside the function body is an exception to the rule about running Python code from the top to the bottom of the file. That code is stored away and then executed later when we tell the function to run. Like the code in a file, the code in a function runs from top to bottom, one statement or expression at a time. If you're more familiar with C++ or Java, you may be wondering where the function parameter types and return types are. In Python, the data type is inherent in each data value, so the runtime always knows what type of data we're working with and whether what we're trying to do is a valid operation for that data type. Thus, for the most part, we don't need explicit data types. Python programmers sometimes talk about duck typing, which is a reference to the saying that if it quacks like a duck, it's probably a duck. What they mean by that is that if the operations we're trying to perform on a data value work, it doesn't really matter if it's precisely the kind of data we expected. It's probably close enough. If they don't work, Python will tell us what went wrong and where, which is often more useful to know than the kind of information that can be determined by comparing data types alone. For those situations where we do want or need to specify data types, we can use function annotations and the standard library typing module. Function decorators, which we'll discuss later in the course, can provide a convenient way of enforcing these annotations. The second major building block of a Python program is called a variable. A variable is pretty much just a box for storing a data value. The variable has a name, and we can use that name to access the data stored in the variable, or to replace the data with a new value. The function parameters in the previous examples were variables, as was the area. To set the data stored in a variable, we use an assignment section. This is a statement, so it can't be combined with any other statement. It gets a line of source code all for itself and the expressions that are part of it. An assignment statement consists of the variable's name on the left side of an equal symbol and the value we want to store in the variable on the right side. If the variable didn't already exist, it is created. Whether or not the variable existed before, the value is stored in the variable. Variables that are created inside a function are only visible inside that function, and each time the function runs, they are created anew. The last line of this example demonstrates that the variable created inside the function does not exist for code outside the function. It also shows what happens when we try to ask Python to to do something impossible. It tells us what we did wrong and gives us information about where the problem occurred and how we got there. The third major building blocks of Python program are expressions. We've seen expressions in every example so far because it's nearly impossible to do anything without using expressions. Expressions consist of data values and operations to perform on those data values. The very simplest expressions are a single data value and no operations. For example, a single number. More complex expressions involve at least one operation and probably more data values as well. For example, adding two numbers. All expressions produce a resulting data value of some sort. Adding two numbers produces the sum as another number, while concatenating two text strings produces the concatenation as another text string. Using a variable name to look up the stored value is an expression. So is running a function. If the function doesn't explicitly return a value, a special value called none is the result. Anywhere we need a value, we can use any expression that produces the needed value. It doesn't matter whether the expression is a simple number like 55, or a variable name, or a complex combination of values and operators, or a function call, or any other expression. At least, it doesn't matter as far as the final result is concerned. Some expressions take less time to execute than others, so speed can be a factor. The final fundamental building block we're going to discuss here is classes. The word class is a synonym for category or type, in this case, referring to data values. A class defines a new kind of data value by describing a set of internal data and operations for that type of data value. This is done primarily by defining a group of functions that make up the class. A special function called _init_ is used to set up the internal data for a new data value of this type, and the rest of the functions define the operations on an existing data value of this type. All the functions of a class receive a parameter called self. That parameter is the data value being operated on. That's different from C++ or Java because while those languages do basically the same thing, the parameter is implicit instead of being an explicit part of the function's parameter list. Class functions, including _init_, should store and retrieve data from self when they want to manipulate the data value that they're connected to. Classes are support inheritance and multiple inheritance, but we're not going into that here. In this example, we've created a new data type called fruit, and then made two separate data values of that type. Then we use the anniversary function that we created as part of the class to modify each of them. Notice that the two instances maintain their internal variables with different values. Python has several flow control statements that will be familiar to people who know another language in the C family. For example, Python has loops and if, elif, else branches. Python also has a for loop statement, but it's not like the for loops in C, C++, or Java. Instead of counting through numbers, the for loop iterates through values. If we actually want to count through numbers with a for loop, that's easily done using a range. Iterate R. There's one last thing I should comment on before we wrap up this video, and that's Python's use of indentation to signify block structure. Most other programming languages have explicit symbols that mean beginning of a block and end of a block. However, it's a common practice in all of those languages to indent blocks, so humans find the code easier to read. In fact, failure to do so is often taken as a sign that a programmer is an amateur. That means that the block structure is actually represented in two different ways in most languages. By making the indentation into syntax, Python both removes that duplication and ensures that the code is readable. With that, we've come to the end of this video. In the next video, we'll look at some of Python's built-in data structures and data processing syntax. In the previous video, we looked at some fundamentals of the Python programming language. In this video, we're going to take a look at the core data structure, types, of Python. These aren't the only data structures available, of course, because it's fairly easy to create data structures using classes. However, these data structures are built right into the heart of Python, and they're highly efficient. It's a good idea to be very familiar with them. The first thing to understand is that data structures are themselves data values. Like a filing cabinet, they're one thing that contains many things. Like any other data value, they can be stored in a variable or used as part of an expression. The first data structure we're going to look at is Python's dictionary. A dictionary consists of any number of key value pairs. The key could be used to get or set the value or remove the pair from the dictionary entirely. Similar data structures in other languages are sometimes called maps or hash tables. There are several ways to create a dictionary in Python. The simplest is to use a dictionary expression, which is just a pair of curly brackets surrounding the key value pairs we want. In the dictionary, each key value pair is marked by a colon between the key and value, and each pair is separated by a comma. When this expression runs, the result is a dictionary object containing the keys and their values. We can also use the dict class to create dictionary objects if we don't want to use the special syntax. To access one of the stored values in a dictionary, we use a lookup expression, which means we place square brackets containing the key we want. We want to look up after an expression that gives us the dictionary. Usually that means the name of the variable containing the dictionary. An open square bracket, a sub-expression that gives us the key, and then a closing square bracket, like this. We can also use the dictionary's get function if we prefer not to use the special syntax. The next data type we're going to look at is a list, which can be created with a list expression. A list expression is just a pair of square brackets surrounding the data values we want to store in the list, with each value separated by a comma. It is not necessary that each of the values be of the same type. In this example, they are strings of list, but they could be numbers or list or any other kind of data mixed together. We can use a lookup expression to retrieve data values. Unlike with a dictionary, though, the keys for a list are integers. That's because instead of associating key values with data values, a list just stores its data values in order. The key for the very first item in the list is 0. 1 is the key for the next item, and so on. We still get a data value out, but it's counted from the end of the list instead of the beginning, with the item at -1 being the last item in the list. We can use the list append function to add a new item at the end of the list, or its insert function to add a new item anywhere. The list will automatically grow to be large enough to hold all of the data we put into it. The next data structure we'll look at is the tuple. A tuple expression is any sequence of value expressions separated by commas. If it happens in a place where the language wasn't already expecting to see a comma. However, it's common and smart to put parentheses around most tuple expressions because it avoids ambiguity. Like a list, data values can be retrieved from a tuple by using numbers. Unlike a list, we can't add more data to a tuple, nor can we replace one data value with another. Why would we want a data structure like that? Well, there are several reasons. First, because they are constant, tuples make good dictionary keys, or set members, but we'll get to that in a bit. Second, they fill a different conceptual role than list. We tend to expect every member of a list to be the same type, like a list of names or a list of ages. Lists are sort of like columns of a database in that way. We tend to expect tuples to contain different types of data in each element, but we expect them to be related to each other, like a name in the first element and an age in the second. To continue our analogy, tuples are something like rows in a database. Third, tuples tend to be slightly more efficient for the computer to work with, both in terms of time and memory usage. So in optimization situations, they're preferable to lists when they're sufficient to the task. The final data structure we'll look at is the set. A set is a collection of data values without keys, like a list, but in no particular order, like a dictionary. We can create a set using a set expression, which is a pair of curly brackets around comma-separated values. Locating a specific value in a set is fast, as is adding or removing a value. Each value can only be in the set once. Sets support a bunch of mathematical operations like union and intersection, and are generally more useful than might be obvious at first, though we don't really have time to prove that here. Python has a special kind of expression called a comprehension. Comprehensions are variations of the special syntax for creating dictionaries, lists, and sets. Let's look at some examples. Here we see a list comprehension. What this expression does is create a new list containing the uppercase versions of the words in the old list. The first part after the opening square bracket is an expression describing how to derive a member of the new list from a member of the old list. After that is the keyword for, then name of the variable we used in the first expression to represent the values from the old list. Then the keyword in, followed by the expression that gives us the old list and the closing square bracket. As you can see, dictionary and set comprehensions are very similar. If we want to use both the key and the value of an existing dictionary in a comprehension, we need to use the dictionary's items, function, and dictionary comprehensions need to specify both key and value separated by a colon. Also, notice that the resulting data type depends on what sort of comprehension we used, not on what sort of data structure we used as the source of data. We can use a list comprehension to create a list of data pulled from the values of a dictionary. For example, or as we did here, we can use the set comprehension to create a set. Tuples are slightly different, but only slightly. A tuple comprehension would look exactly like a different syntactic element called a generator expression, and Python's designers hate ambiguity. So instead, if we want the equivalent of a tuple comprehension, we pass a generator expression to a tuple constructor. That's it for this quick introduction to Python's built-in data structures. In this video, we have seen how to create and access those data structures, and how to use comprehensions to create transformed data structures based on existing ones. In the next video, we're going to look at some useful but possibly surprising traits of functions and classes. Hi, and welcome back. In the previous video, we looked at Python's built-in data structures. In this video, we're going to take a look at a feature of Python that is significantly different from C, C++, or Java. In Python, functions and classes are first-class objects. The phrase first-class object is a fancy way of saying something is a data value that can be accessed, modified, stored, and otherwise manipulated by the program it's a part of. In Python, a function is just as much a data value as a text string is. The same goes for classes. When a function definition statement gets run, it stores the resulting function in a variable with the name that was specified in the def statement. That variable isn't special. It's just like any other variable holding a value. That means we can use it in expressions, assign the value to other values, or even store a different value in place of the original function. The function value itself contains quite a few attribute variables which we can access. More usefully, most of the time, we can add attributes to a function object, allowing us to store custom information about a function as part of the function and access that information later. One common task that first-class functions make easy is assigning handlers to events. To bind a handler function to an event in Python, we just pass the function object as a parameter when we call the binding function. That's a significant improvement over the hoops that C++ or Java imposes on us to do something similar. Like function definition statements, class definition statements create a class object and store it in a variable. That can be confusing at first. Classes describe a type of object. How can they be objects themselves? Think of it this way. A blueprint for a house describes a type of building, but the blueprint is still a thing in its own right. It's the same with class objects. This means that like function objects, class objects can be stored in variables and otherwise treated as data values. Most interestingly, they can be used as parameters to function calls. As an example of why that's interesting, consider this. Python's standard library contains a data structure class called default_dict, which is like a dictionary, except that when we try to look up a key that isn't already in the dictionary, it creates a new value and adds it to the dictionary before returning it to the code that tried the lookup. How does a default_dict know how to create the default value? It knows because we gave it a class as a parameter when we created the default_dict. Thus, if we want a dictionary of lists, we could give the default_dict the list class as its how to make a default parameter. As an aside, default_dict can also work with a function as its how to make a default parameter. The default_dict actually doesn't care what that parameter is, as long as the object we passed can create a new object whenever the default_dict needs a new default. That's an example of the duck typing we mentioned in the previous video. It doesn't matter whether the parameter is a function, a class, or anything else, so long as it behaves properly. If it doesn't behave properly, we'll be told what went wrong and where. We saw a little while ago that we could add attributes to function objects, which is often handy. We could do something similar with classes with one big difference. Attributes we add to functions are only visible to code that has access to that function object, which usually doesn't actually include the code of the function itself. Attributes we add to class objects are visible to any code that has access to the class object or to an object of the type described by the class. That means that if we add an attribute to a class, the functions defined in that class will be able to access that attribute through the self parameter. We need to be careful when adding attributes to classes, because if we accidentally overwrite one of the class's attributes, we could break the class. We have a greater ability to manipulate classes than functions, so we need to use that ability more thoughtfully. Also, notice that in this example, one of the attributes we added to the class is a function, which then proceeds to work exactly as if it had been defined as part of the class from the beginning. In this video, we have looked briefly at what it means for Python to have first-class functions and classes and how that can affect the possibilities open to us as programmers. In the next video, we'll take a short tour of some of the highlights of Python's standard library. Welcome back to a brand new video in this section. In the previous video, we looked at what it means that Python has first-class functions and classes. In this video, we're going to briefly talk about some of the high points of the Python standard library. The library of code that comes pre-installed with Python is extensive, so we're not going to be able to go into detail. The goal here is to come away with an understanding of the breadth of quality tools we have available, so if we need them in the future, we know where to look. Thus, we're going to just briefly touch on many useful things. First off, there is the collections package, which contains even more data structures. Collections contains the default dict class that we spoke about in the previous video. The collections package also contains an ordered dictionary that remembers the order in which items were inserted and gives them back in the same order when we iterate over it. A double-ended queue class, a variation on tuples that uses names to access the elements, and a pseudo-dictionary that provides a composite view of several other dictionaries. There are a few other data structures in there as well. One common data structure missing from the collections package is a priority queue, but that's just because it has its own package called heap queue. Python's priority queue operations are implemented as functions that work with built-in lists to add and remove items according to the heap property. Storing and retrieving data is an extremely common need for programs, and the pickle package makes it easy. Inside the pickle package are classes and functions that facilitate transforming arbitrary Python data into a sequence of bytes that can be stored in a file or sent across the network or whatever you need. The pickle package also has the tools to reverse the process and transform those bytes back into fully fledged Python data objects. Also, in the vein of storing data, the SQLite 3 package provides complete access to the SQLite database manager, allowing us to take advantage of a complete transactional relational database. Third-party packages to access other database systems follow pretty much the same interface, so it's easy to make the switch to a different database later if needed. Also, relevant to data handling is the JSON package, which parses or generates the de facto standard Internet Data Exchange format. The JSON package is smart, so it handles JSON objects, arrays, strings, numbers, null values, and so on in a sensible way, mapping them onto the proper Python data types. The base64 package encodes bytes into base64 or decodes base64 into bytes. There are several other similar packages for bin hex, ucode, and so on as well. The HTML and XML packages provide all sorts of utilities for dealing with the major internet markup languages, including parsers and document object models. The URL lib package provides us with convenient ways to retrieve data from URLs or to send data to them. In particular, the URL lib.request .url open function is extremely useful. The itertools and functools packages provide an assortment of utilities having to do with functional programming paradigms. In particular, the functools package allows for us to create partially applied functions, and the itertools package lets us concatenate iterators. The enum package contains support for creating and using named enumerations. Each enumeration is a distinct data type, like a class. The pathlib package contains classes and functions that provide a cross-platform abstraction of file and file path operations. The inspect package is interesting and quite useful. It provides us with functions that can be used to gather information about data objects, particularly about functions and classes. If we want to know the names of functions parameters or we want to access an object's documentation or any number of things along those lines, the inspect package will get us there. The packages we've just looked at are by no means the complete list of what's available in the standard library, but hopefully they give some idea of the depth and breadth of what we get just by installing Python. Taking a look through the library documentation on python.org is highly recommended for people who want to get the most out of Python. There are some particularly useful packages that we didn't mention at all. That's because there are whole videos or even course sections devoted to them later. So that brings us to the end of our overview of the standard library. In the next video, we're going to take a look at what's new in Python 3.5 specifically. Hello, and welcome to the video New in Python 3.5. In this video, we're going to take a look at the changes in Python version 3.5 specifically. The syntactic changes, the changes in the packages, and a bunch of other changes as well. Let's get started. Python 3.5 has 3 new groups of syntactic additions. The first of those groups is the introduction of keywords for describing coroutines. Python already supported coroutines, but the keywords make things clearer and sometimes simpler. We'll be talking about coroutines in depth in a later section, so we won't go into this any further just now. The second piece of new syntax is the introduction of the @ symbol as an infix binary operator. That means that placing an @ symbol between 2 sub-expressions is now a valid Python expression, just like placing a plus symbol between them would be. However, since no built-in data types support the @ symbol operator yet, we won't be finding much use for it in this course. Intended semantic meaning of the @ symbol is that it should represent matrix multiplication, and it was added to improve support for and interoperability between third-party packages that implement matrices and matrix operations. The third piece of new syntax is an expansion of Python's pre-existing syntax for using lists and dictionaries to provide the parameter values when invoking a function. Before it was possible to put an asterisk before a list of values to indicate that those values should be assigned to the parameters in the same order that they appeared in the list, or similarly to use 2 asterisks to indicate that the values in a dictionary with text string keys should be assigned to the function's parameters by name. The new syntax is just that we can now use more than one list or dictionary in this way, and that we can use the same asterisk and double asterisk syntax for constructing tuples, lists, dictionaries, and sets. We mentioned earlier that while Python attaches data types to data values rather than variables, it is possible to use function annotations to describe the expected types of function annotations, of function parameters, return values. Python 3.5 now includes in the standard library a package called typing that contains classes and functions supporting that usage. Python 3.5 now includes a package called zipapp in the standard library. This package makes it easy to construct .pys files. .pys file is an archive file containing Python code and arbitrary read-only data, which the Python runtime is able to execute as a self-contained program. Once a program is debugged and ready for distribution, packaging it into a .pys file is a simple and smart way to hand it to the users. There are some low-level improvements in Python 3.5, like faster reading of file system directories, automatic retrying of interrupted operating system calls, and a math.is close function for checking whether 2 numbers are approximately equal. There are also a bunch more minor additions that improve things throughout the standard library, all backwards compatible with earlier Python 3 versions. In the rare cases where something is added that breaks backwards compatibility, it's not enabled by default. For such a change, if we want to use it, we'd have to specifically mark our code as supporting the change. Those changes will not become standard until Python version 3.7, with Python 3.5 and 3.6 issuing warnings when they encounter code that depends on the changing feature. In Python 3.5, there is only one such change, a small and smart alteration in the iteration protocol. It shouldn't have any effect on code that works properly, but technically, it's a change in the interface, and so it gets the full wait 2 versions treatment. If you want more detail about any of these changes I've mentioned, or if you ever want to find out what's changed between versions of Python, the documentation on docs.python.org always contains a What's New document that goes into some detail about new features and provides links to the full documentation. I always look forward to reading the What's New document for each release of Python to find out what new toys I've just been handed. So, we've now had a high-level view of the Python standard library, introducing us to some of the more useful items it contains. That brings us to the end of our Python primer. In this section, we've quickly covered the syntax, basic assumptions, and fundamental tools of the Python programming language. In the next section, we're going to see how to set up a Python programming environment for us to work in for the remainder of the course, and learn a bit about how to integrate third-party code. Join me there. Hi, and welcome to a brand new section of our course that helps with setting up and getting familiar with the Python programming environment and tools. In the previous section, we took a brief tour of the Python programming language. In this section, we're going to look into various ways to download and install the right version of Python. Then we're going to see how to run Python code. In the last couple of videos of this section, we'll look at how to begin taking advantage of the wide variety of publicly available Python code available on the internet. In this first video of the section, the topic is downloading and installing the Python runtime and standard library. We're going to take a look at the python.org download page, which is, of course, the authoritative place to find Python. We're going to learn a little bit about which versions of Python exist and which we should choose for the course. Then we'll move on to how to set up for this course. Finally, we'll check that everything worked the way we wanted. Before we can really begin working with Python, we need to make sure we've got the language interpreter and libraries properly installed. The first step of that is to decide which version of the language to install. There are currently 2 common varieties of Python in use. One of them is Python version 2.7, which is the final version of the Python 2 series. The Python community has promised to maintain version 2.7 indefinitely, making it a very stable target for development. The other common version is Python 3, which at the time of this recording is in version 3.5. Python 3 is where the Python community is innovating. The releases are always backward compatible with earlier version 3 releases. But exciting new features are added regularly. During the change to version 3, the language and libraries were changed in subtle ways, as you can see by comparing these 2 code snippets. On the left is Python 2. On the right, you see equivalent code in Python 3. It's almost the same, but there are differences like placement of parentheses, a few keywords, and slightly different structure to the standard library. You're free to pick whichever version or versions you want for your own projects. But for this course, we'll be using Python version 3. Now that we picked a version, let's install it. If you're a Windows or Mac user, you could download an installer directly from the Python website. Pick the installer appropriate for your computer, download it, and run it. For any platform, we also have the option of downloading the source code, compiling it, and installing Python that way. Unix and Linux users, including Mac users who prefer it, have the option to install Python through their package manager instead. For systems which integrate a package manager, this is probably the best and easiest choice. If we used a package manager, this next part is probably already done. Otherwise, we need to make sure that the Python programs are able to run from the command line on Mac OS X and Unix-like operating systems. All we need to do is add a line to the profile or bash rc file in our home directory. Windows is only slightly more involved. In each of the examples on the screen, pydir is the directory where you installed python:// python35, for example. Once we've got the path environment variable set, we should be good to go. To check that, open a terminal window and type Python, then hit enter. If you don't know how to open a terminal, don't worry. We'll talk about that in more detail in the next video. Also, if you are a Unix user and you do not receive the correct result, it is potentially because the bash rc or profile has not been executed yet. You may need to log out and log back in again. If the Python interactive shell starts up, when we type Python into the terminal, we're good to go. If it doesn't, go back and double check the changes that we made to the path environment variable, because that's the piece that tells the operating system where to look for programs. That's it for setting up. If you're feeling adventurous, you could experiment with the interactive shell that we just started up. Try typing in mathematical expressions and see what happens. In the next video, we'll look more closely at running Python code using the command line and the interactive shell. In the previous video, we looked at installing Python. In this video, we're going to try our hand at making Python actually do things using the textual interface. Text-based user interfaces are highly useful to programmers. They provide a quick and easy way to interact with programs while they're in development, experiment with code, which is, after all, text, and access documentation. How you open a command line window depends on the operating system you're using. On Windows 7, open the Start menu and type CMD into the Run box. On Windows 8, press the Window key and then type CMD. On Command Prompt, on Windows 10, press the Window key and select Command Prompt. On Mac OS X, run Applications, Utilities, Terminal. On Linux or other Unix-style operating systems, the precise mechanism for opening a command line window varies, but they all have the ability to do it. Look for the words xterm, terminal, or shell. Now that we've got a command line, we're going straight into the Python interactive shell. We do that by typing Python into the command line window. If you have multiple versions of Python installed and we want to interact with a specified version, we can explicitly choose the version from the command line by typing in that version's name. For example, if we type Python 3, we'll explicitly start up some version of Python 3.x. Here's where the fun really starts. When we see the triple greater than prompt, we could type in any Python expression or statement and see the result immediately. That's incredibly useful because it means we don't have to remember every detail about how functions work, what class members are called, which exceptions are raised, under what circumstances, and so on. Whenever we're unsure about something, we could just open up an interactive shell and find out. So for example, let's imagine we're working on an application that uses Python's setDataType, and we're unsure about what exception gets raised when we try to add a set to itself. We could go digging through the documentation, but it's quicker and easier to just create a set in the interactive shell and try adding it to itself. Right away, the system tells us that adding a set to itself raises a type error exception. Sometimes, running a quick experiment in the interactive shell is the fastest way to get information we want. But documentation is nice too. Fortunately, Python has a very good documentation system that we can access straight from the interactive shell by calling the help function. We could pass any object as the parameter of the help function, and it will print out that object's documentation for us. So, if we want to find out about the functools.wraps function, we just pass it to help and read all about it. The help function can also take the name of the object you want to read about instead of the object itself. That could save us the time of typing in an import statement in the interactive shell. The difference is that the help parameter is a string, not an expression that evaluates to the object we're interested in. In this video, we've examined how to make the best of Python's command line and its extensive help library. In the next video, we'll examine how to handle third-party packages. In the previous video, we looked at running Python in a command window and using it to perform experiments and calculations. In this video, we're going to take a look at using Python's package manager to install and manage third-party code. And now it's back to the operating system command line for us. We're going to see how to easily install third-party code from the Python package index. While Python comes with batteries included, meaning that the Python standard library that's already installed contains a wide range of very useful features, there's still plenty of things it doesn't do. Odds are, though, that somebody somewhere has already invented the wheel for us, and if so, we could probably find it in the Python package index. Python 3.4 and later are installed with a tool called pip, which can interface with the Python package index to automatically find, download, and install Python packages. If you already know the name of the package you want and you have permission to write into Python's library directory, then this relatively simple command will get it fully installed and ready to be used. In this instance, we installed a package called bank number, which check if someone's bank number is a valid bank number or is just a random number. If we don't have permission to Python's library directory, never fear. Python will look for a second user-specific library directory, and since that library directory belongs to us, we'll always be able to install packages there. To tell pip that we want to install into our personal library directory, just add --user to the command right after install. Pip could do more than just install packages. It can also give us a list of currently installed packages, upgrade currently installed packages to the newest version, and uninstall packages that we don't need anymore. In short, it's a complete cross-platform management tool for Python packages. Some Python packages require that we be able to compile extensions written in the C programming language to install them, but fortunately, that's becoming rare. Normally, if a compiled extension is required, pip will be able to find and install the proper pre-compiled version automatically. The majority of available packages are pure Python anyhow and don't require compilation. Pip has great many more options and command line switches, but what we've seen so far covers the common situations well. If you want to dig into it further, pip's help command will give you the details. For example, this command prints out all the information you could possibly want about the pip install option. In this video, we figured out how to install third-party packages that cut to the chase and make life much easier. In the next video, we'll see how to sift through the Python package index and find the packages that we need to install. Welcome back. In the last video, we saw how to use pip to install packages. In this video, we're going to take a look at how to find packages that we want to install. We've talked about installing packages from the Python package index. But what if we don't have a specific package we need to install? What if we just need a library to to help us get the job done, but don't know which specific one we need? Well, as the name implies, the Python package index is actually index of packages, which classifies them according to a number of parameters. We could search the available packages in a number of ways. The index is conveniently hosted at pypy.python.org. Perhaps the most useful way of accessing the index is to simply type keywords into the search box and see what it spits out. If we ask it to search for asyncio, we get back a collection of package names that have something to do with asyncio. The names are, of course, links to each package's detailed description on the index, which we can use to decide which package best suits our needs. There's another way of accessing the index that is often nearly as useful as keyword searching and sometimes even more useful. The Python package index supports browsing through its index of packages by category. You start browsing by clicking the browse link in the menu, which brings you to this list of different categories. From here, you could select one or more categories by clicking on them and be shown a list of the packages that fall into all of your selected categories if the list is short enough to be useful. If you don't get a list of packages, it's because the list would be so long that it wouldn't do you any good, and you should select more categories to narrow it down. If a category disappears from the list while you're selecting, that means that there are no packages that are in all of your selected categories, and in that one as well. Of particular note here are the natural language categories. Python is not only written in English, and not only used by people who prefer that language. Some packages have good support for other languages, and this list is a good way to find them, whereas keyword searching might not pick up on that kind of detail. If we don't want to fire up our browser to go searching through the index, we can also do it from the command line through pip. This command performs the same search that we did earlier through the web interface. Doing it this way is often faster, but as you can see, it only provides us with a name and a brief description of each package. This is perfect for getting a quick reminder about what a package is named, but not so good for more in-depth research. Finally, a quick note about legalities and licenses. The vast majority of packages in the Python package index are under open source licenses, as certified by the Open Source Institute. That means, basically, that they can be freely used and distributed as part of other open source projects. In most cases, the licenses are more liberal than that, allowing us to use the software as part of our projects, even if we don't open source our own code. Most does not mean all, however. Some of the packages are not under OSI certified licenses, and some of the OSI licensed packages are not usable in closed source projects. If you're going to be distributing your software, take a moment to make sure the licenses line up with your goals. So, now we have a pretty good idea of how to find third-party code to help us move our projects along using the Python package index. In this section as a whole, we have learned how to install Python and get ourselves to a place where we can begin working on real code. In the next section, we'll work through the steps to create and work with our own Python code packages. Code packages. Hi, and welcome to Section 3. In the previous section, we saw how to install Python and third-party packages of code that we can use with Python. In this section, we're going to look at how to create our own packages of Python code. Packages will form the basis for programs and help us to make our code modular. We will look at creating packages, adding modules to package, accessing code from other modules, and adding static data files to the package. Now we move on to the first video of this section that deals with creating a simple empty package. It won't do anything yet, but by the time we're done, we'll be able to import it into the Python shell. In this video, we're going to take a look at how packages are represented on the computer's file system. Very simple. Python projects may consist of a single code module, but normally there are multiple modules combined together into a package. A package can contain as many modules as we need it to. Packages start their lives as folders on the file system, which means we can make them just as we would make any other folder. If you prefer to use your operating system's file browser to make folders, that's fine, but I usually use the command line. There are two things that turn a regular folder into a package. The first of those two things is where it is. Python only looks in certain places for packages, and if your folder isn't in the right place, Python won't notice it. The sys.path variable contains a list of all the places Python will look for packages. The sys.path I'm showing here is fairly sparse, but user configuration can make it much more extensive. Notice that the first entry in the list is an empty string. That stands for the current working directory. For those of us using the command line, the current working directory is just the folder we're currently in. We could change the current working directory with the cd command. Cd dot means go back to the previous directory or the parent directory. So I went into and out of demo package. The fact that the current working directory is in the path is convenient during development. It means that we could just set the current working directory to the place where we're doing our development, and all of our packages become available, at least as long as we also use the command line to launch Python. The second thing that turns a regular folder into a package is the presence of an underscore init underscore.py file, underbar, double underbar. Though not strictly necessary since Python 3.3, an init file marks the folder as a package, which makes it load more efficiently, and also gives us a place to put information and code relevant to the interface of the package as a whole. While it's quite common that the init.py file is completely empty and serves only as a marker, there's one language feature that won't be supported unless we add a little code to the file. That feature is the ability to import all of the package's modules using the import star syntax. If we want Python to be able to do this, we have to tell it what we mean by all of the package's modules. To do that, we add the module names to a list called underbar all underbar underbar in the init file. You might be wondering why we need to do this manually rather than Python just scanning the file system for module files. There are a couple of reasons. First, Python tries not to make any assumptions about whether file names are case sensitive or not. On some operating systems they are, and on others they're not. Module names are variables, so it's better if they originate within the source code rather than depending on something external that might change depending on where the code is run. The second reason for doing this manually is that importing a module makes code execute. Imagine we have a package that plays soundtracks. In addition to the general purpose code, we also have a bunch of modules that handle audio output on various systems. It's quite reasonable to allow our users to do an import star to bring their package's programming interface into their module, but we don't want all of the output modules to load, just the one that's appropriate to the system we're running on. Trying to load any of the others would most likely trigger an exception in the user's code. The way underbar underbar all underbar underbar works now, we can exclude the output modules from the import star and get the best of both worlds. Alright, let's make sure that Python is willing to import our demo package, and then we'll move on to how to add source code modules to a package. In this video, we've learned how to create a Python package as a directory on the file system, and how to mark it with an init.py file so that importing is efficient and we can add package metadata. In the next video, we'll see about adding code modules inside the package. Hello and welcome back. In the previous video, we looked at how to build a package out of the directories and files. In this video, we're going to look at adding actual code to the package and add a couple of pitfalls to avoid. Python modules have the same name as objects that they have as file names, except without the .py suffix. That means that the file names need to be valid Python variable names, and also that they should use letters and symbols that are reliably available across different operating systems. So, as examples, module names should not start with a number because Python variables are not allowed to start with numbers, and should not use capital letters because some common operating systems don't differentiate between file names containing capital letters and file names that are all lowercase. As long as we stay within those guidelines and remember to use a .py suffix, we can name our modules anything we please. So, we just pick a file name and start writing Python code into a file with that name in the package folder. That simple scenario is also the common case, but there's another possibility. As we've mentioned before, starting in Python 3.3, it's possible to have a package folder that doesn't contain an init file. Leaving out the init file means we can't support import star or the other tricks within it that we'll discover as we go along. But there's more to it than that. When the init file is missing, the folder becomes part of a namespace package. When Python is importing, it combines all of the namespace package folders it finds that share a name into a single logical package. That behavior means that while choosing the module file name still follows the same rules, we could potentially place that file into one of any number of namespace package folders instead of into a singular, concrete package folder. What do we gain from that? Often nothing. As I mentioned before, packages with an init load faster, and in many cases, the extra abstraction of namespace packages doesn't buy us anything. There are cases, however, when we want different parts of the same package to be distributed or managed separately, and when we do, namespace packages address that need. For example, imagine again that we're working on a package for playing soundtracks. If we make a namespace package for audio codecs, each codec can be installed and removed individually using pip, or the operating system's normal package management tools. On a slightly different topic, now let's talk about the difference between how a package is structured and the interface it should present for use by external code. For the convenience and sanity of ourselves, as the package developers, it's often best to break up the code in a package into many different modules that each contain a selection of conceptually related code. That is the package's structure. And as a rule of thumb, whenever we think we might want to break the code up into more modules, we probably should go with that impulse. On the other hand, external code calling on our package is best off when it can take advantage of our code with just one or two import statements that bring in a small number of functions or classes. That is the package's interface, and as a rule of thumb, it should be as minimal as possible while preserving full functionality. Fortunately, we can have our cake and eat it too. We can divide our code up however we wish and then import the most useful elements into our init file, which will make them part of the package's root namespace. If all that's in init file is import statements, we don't need all variable. An import star will grab the contents of the init file, except for variables, starting with an underscore. However, if we define or import anything in the init file that should not be part of the public interface, we can use the all variable to narrow down and control what we export. Just remember, if we have an all list, it needs to list everything that is part of the package's interface, whether a module, class, function, or variable. The rest of the modules in the package are still available to be explicitly imported. We're just making it convenient to access the parts that are most likely to be useful outside our own package. Now we have a good idea of how to name our modules, where to put them so that they become part of our package, and how to give our package a convenient interface. In the next video, we'll move on to looking at how to make the modules in a package interact with each other. In the previous video, we looked at adding code modules to a package. In this video, we're going to take a look at how to make those code modules interact with each other within the package. We'll start off by understanding the difference between absolute and relative imports, then moving on to writing those, and finally, we'll look at cyclic dependencies. When we're importing one of a package's modules from outside the package, there's only one sensible way that it could work. We tell Python which package and module we want, and it either finds and imports it or raises an exception if it can't. Simple. When we're already inside a package, the situation is more ambiguous because import name could just as easily mean look for name within this package, or look for name in the Python search path. Python breaks this ambiguity by defining import name to mean that a package or module called name should be searched for in Python search path, and by giving us a way to specify a relative import if we'd rather have it just look within the current package. We could specify a relative import by putting a dot in front of the name of the module we want to import. When Python sees that, it will look for a module called name in the same package as the module our code is running in. Often, we only need one or two objects from another module, and it's more convenient to import those objects directly into our global scope than it would be to import the module as a whole and access its contents. Python lets us do that with a slight variation on the import syntax. Finally, sometimes we want to rename an object within our scope as we import it. We can do that by modifying our import with the keyword as. In this example, even though the object is called foo in the name module, in our current module it's named bar. This trick works for absolute imports too, by the way. Before we move on, let's take note that Python 2 used a different rule for deciding where to find imported code. In Python 2, it first tried to find the target of an import within the current package. Then, if no matching module was found there, it went out and looked for it on the search path. That approach usually did the right thing, but occasionally caused problems due to the ambiguous meaning, and it meant that we couldn't have subpackages, or modules that shared the name of anything in the standard library or other installed packages. So, this behavior was changed in Python 3. There's something that might trip us up when we're importing a module that shares the same package. Sometimes the module we're importing wants to import us as well. This is called a cyclic dependency. When we try to import a cyclic dependency, we'll almost always get an attribute error exception, as in this example. That happens because when we ask Python to import the first module, Python immediately creates a module object for it and begins executing the code in the module. That's fine, except that when Python gets to the import statement for the next module in the cycle, it pauses running the code in the first module, leaving it not fully initialized. Even that isn't normally a problem because Python will come back and finish the initialization later. However, when the second module asks to import the first module, Python just hands it the already allocated and not fully initialized module object. When the second module tries to access the variables stored in the first object, many of them will not yet have been created. Hence, an attribute error is raised. There are two common ways to address this problem. The first And usually the best is to break the cycle by taking some of the code from one of the modules and moving it into a third module, which both other modules can import without causing a cycle. In this example, if we move the A class into its own module, there would be no cycle, and all would be well. The other way to address this problem is to move the import statement that causes the cycle. If we move the import statement down until it's below all the variable definitions that are needed by the other modules in the cycle, the module will be initialized enough when it's imported by the other modules. Python will still come back and finish the initialization later. In this video, we've gotten a pretty good handle on how to import modules into other modules contained in the same package. In the next video, we'll move on to adding static data file resources. Hello again. Welcome back. In the previous video, we saw how code modules within the same package interact. In this video, we're going to take a look at how to access data from non-code files that are incorporated into our package. Alright, if we're going to be adding data files to the package, where should we put them? Really, we could put them anywhere. That's convenient within the package folder, but it's often a good idea to create a subfolder, specifically for holding the data files. That keeps data files separate from source code and generally makes them a little easier to work with. I should note here that data files that are part of a package should be assumed to be read-only. There are many reasons that might cause the files to not be writable at runtime. So if we want to write data to a file while our code is running, we need to pick somewhere else to store it. Only files that do not change are appropriate for inclusion in a package. So that said, all we have to do to include a data file in our package is drop it into our package. Drop it into our package and then access the data with the getData function from the package, util package, in the standard library. The getData function takes two parameters, the name of the package we want to get data from and the relative path of the data file inside the package, using forward slashes to separate path components. We pass it those two pieces of information and it returns a bytes object to us, containing the contents of the file. If we want a text string instead of bytes, that's easily done. We just need to apply the proper string decoder to the bytes object, and we'll get back a Unicode text string. This technique will work even if our package has been compressed into a zip file or otherwise hidden away, because it uses the same underlying mechanism that Python uses to load module source code. If Python can find the code, it can find the data file as well. That's all there is to working with static data that's packaged up alongside our code. It's simple and useful. That also brings us to the end of this section. In these videos, we've learned how to put together a Python code package that can be used in a program or distributed to other programmers. Soon, we'll see how to turn a package into a complete program as well. In the next section, we're going to step back a little bit and talk about some best practices for working with Python code. Hi, and welcome. In the previous section, we saw how to put together a Python package of code and data. In this section, we're going to look at some rather simple things we can do that will make our lives as Python programmers simpler overall. In this video, we'll take a quick look at how to format our code so that it'll be easy to read when we come back to it at some later date, or when somebody else has to work with it. We will specifically take a look at the indentation rules, the Python code style guide, and finally, the standard naming convention. PEPs, or Python Enhancement Proposals, are the documents that establish standards in the Python community. Most PEPs describe new features for Python or Python standard library, but a few of them are more nebulous. PEP 8 is one of those. It tells us what the Python community considers to be well-written, readable code. The very first rule of PEP8 introduces is that the rules in PEP8 should only apply when they make our code easier to read. If we're working on a project that was already written with a different coding style, we should use that project style for new code. If we're writing code where the PEP8 rules somehow make the code harder to read, we should ignore them. As Guido van Rossum, the creator of Python, has noted, code is read more often than it is written. It should always be written in a way that promotes readability. When programmers read code, we look at how it's indented to tell us how the code blocks are nested. But most other programming languages use actual symbols to tell the language parser where the block begins and ends. Encoding the same information in two different places is a violation of the basic best practices of any programming language. So, Python omits the beginning and ending block markers, uses indentation to inform the parser as well as the programmer. There is one problem that arises from that though. There are different ways of encoding indentation in a text file. We could use space characters or tab characters, or even a combination of both. The codes we're looking at right now mixes spaces and tabs, which in Python 2 was valid, but a terrible idea, and which in Python 3 is a syntax error. I've configured the editor to highlight tab characters in the light blue color, so we can easily see which indentation comes from spaces and which comes from tabs. To see why mixing spaces and tabs is no good, even when it's allowed, all we have to do is change the tab width. Even though the indentation looked good before, now it's clearly wrong. There's no ambiguity if all indentation comes from tab characters. So, using only tabs is valid, even in Python 3. However, it is the recommendation of PEP8 and the Python community that we always use exactly 4 spaces to indicate one level of indentation. Any halfway decent editor can insert those spaces for us when we press the tab key. There are several more recommendations which we're going to go through quickly here. The code on screen right now demonstrates almost all the PEP8 formatting recommendations, and I'll leave it on screen while I talk us through them. PEP8 recommends that a single line of code should not exceed a width of 79 characters. While this is consistent with displaying the code on a standard text mode interface, the primary reason for this rule in the modern world of widescreens and resizable windows is that it helps with reading. Even in contexts that have nothing to do with programming, layout designers prefer to limit line width. Import statements should be placed at the top of the file with standard library imports first, then third-party imports, then imports from other modules. Within the same project, there should be a blank line between each group of imports. Classes and functions at the top level should have 2 blank lines separating them. Methods within a class should have 1 blank line separating them. Within a function or method, blank lines should be used to indicate separation between conceptual groupings of code. Don't insert extra spaces before or after parentheses, brackets, or braces. And don't insert spaces before commas or colons. Always put a single space on either side of a binary operator, such as plus or divide by. Don't put more than one statement on the same line, which is occasionally possible, but never a good idea. Comments should be written in a human language, using that language's correct grammar. Preferably, that language should be English if you're going to allow your source code into the wild, because that language is common to the majority of Python programmers. Comments should also precede the section of code they describe and be indented to the same level. Every public module, class, function, or method should have a properly formatted docstring. We'll look at what properly formatted means for docstrings in video number 4 of this section. Let's move on to picking names for variables, functions, methods, classes, modules, packages, and so on. The overriding rule of Python naming conventions is that the naming style for an object should make it plain how the object is used, not what the object is underneath. That means, for example, that a top-level function, which is called to create new objects, and which therefore behaves like a class, should be named like a class. Packages and modules should have reasonably short names consisting entirely of lowercase letters, and in the case of modules, underscores. Classes should be named with a capitalized first letter and capitals at the start of every new word within the name. This is sometimes also called camel case. Exceptions should be classes, and so they should follow the class naming convention, but they should also end with the word "er." Functions, methods, instance variables, and global variables should all be lowercase, with underscores separating the words, if they are meant to be internal rather than part of the public interface. Their names should begin with a single underscore. The first parameter of an instance method should always be named self. Named constant values should be written in all capital letters with underscores separating words. And that's it for PEP 8 and the formatting rules that most Python programmers expect other people's code to follow. In the next video, we'll move on to talking about nuts and bolts with a discussion of version control. In the previous video, we looked at stylistic aspects of programming in Python, which will help us to keep our code easy to read. In this video, we switch gears and look at version control, which will help us to collaborate with other programmers and serves as an undo buffer for the whole lifetime of a project. Version control is one of the fundamental tools for programmers in the modern world. It helps us with almost every aspect of a project in one way or another. There are many version control systems, and each of them is a topic in itself. So we're going to narrow our focus here and talk about how to do a few particularly useful things using a specific version control system called JIT. The first thing we need to do to use JIT, after installing it of course, is to set up a folder as a JIT repository. That only takes a couple commands on the command line after we move to the folder where we want the repository to be, JIT init and JIT add. Once we've initialized the repository, we add any files that we've already created to it with JIT add. And then we create our first save point in the code with JIT command -a. The -a commit command tells JIT to commit all the changes that have been made. In the future, if we add new files to the project, we should also use JIT add to tell JIT to start tracking them. Anytime we want JIT to remember the current state of our project, we run JIT commit -a again. The nice thing about having old project states saved away is that we could go back to them. If we want to revert a file to a previous state, undoing everything we've done to that file, since a particular commit, we just use the JIT log command to find the identifier for that commit. And then we use JIT checkout to undo our changes. If we later change our mind, we can redo the changes in the same way. The ability to undo on the project level is great, but it's even more useful to make provisional changes to our code and then decide once the changes are done whether or not we really want them in our main code. That's what branches are for. We can make a new branch with JIT checkout-b, which will create the branch and switch to it automatically. When we're in the branch, any code changes we make are associated with the branch, and when we leave the branch, they go away. Then, when we re-enter the branch, they come back. That means we can work on bug fixes in our main branch while we work on new features in their own development branches. When we're finally happy with a feature, we can merge it into the main branch. To merge code from a different branch, all we have to do is use the JIT merge command from inside the branch we're merging to, and give it the name of the branch we're merging from. If the two branches cannot be automatically combined, JIT will do it for us. That's usually all there is to it, but sometimes they're overlapping changes, both branches, and when that happens, JIT knows it's not smart enough to handle the merger on its own. When we run JIT merge, it will notify us that there are conflicts. Then we can use JIT merge tool to start up an interface that lets us use our greater intelligence to resolve the conflict. Once that's done, we use JIT commit to finalize our changes. Merge tool is a smart command that looks for several different tools that exist on various operating systems and picks one of them that hopes is the best choice for you. In this case, it has picked a tool called meld, which is also written in Python indecently for me to use to fix the ambiguity. JIT could do something very similar to combine code from other repositories into our own. The command for that is JIT pull rather than JIT merge, and instead of a branch name, we provide the URL or path name to a different repository. But otherwise, it functions in the same way. This is an incredibly useful feature because it allows us to easily collaborate with other coders, both locally and around the world. In this video, we learned enough about JIT to get some big benefits from using it. In the next video, we're going to look at Python's built-in virtual environment tool, venv. Hello again. In the previous video, we took a look at how to get some big benefits from the JIT version control system with minimal effort. In this video, we're going to look at Python's built-in venv tool, which allows us to keep our programs and their dependencies separate from each other, and the software installed on our overall system. When we're working on a project, we'd usually like the parts of the project that aren't our own code to stay the same. We might have a good reason to install a new version of Python or an updated library on our system, but we don't really want those things to change within our development environment. Even more so, we can easily find ourselves targeting entirely different and incompatible system configurations with different projects. We need a way to set aside an area for each project that is separate and can be configured for the specific needs of that project. That's what we call a virtual environment. And the venv tool that's built in to Python 3.3 and later creates them for us. Each virtual environment created by venv knows which version of Python it should be using and has its own package library, which means that as far as Python code is concerned, it's basically disconnected from the rest of the system. We can install, uninstall, and update packages on the system, and the code inside the virtual environment won't even notice. We can install new versions of Python, and the code inside the virtual environment won't notice. About the only thing we can't safely do at the system level is uninstalling the version of Python that the virtual environment is based on. It's easy to create a virtual environment for a new project. We just open the command line and go to the folder where we want the project folder to reside. Then we use the version of Python that we want the virtual environment to use to run the venv tool. When we call venv, we tell it the name we want to give to the project folder. The venv tool will create the project folder and populate it with the files needed to support the virtual environment. Each time we actually want to work inside the virtual environment, we should activate it. That will make whatever changes are needed so that the contents of the virtual environment override the system level defaults. To activate a virtual environment, we open a command line and go to the folder containing the virtual environment, then execute the activation command. The specific activation command we're using depends on the operating system. On most Unix-style systems, including Macintosh, we use the command source bin/activate. On Windows, we run scripts /activate.bat. When we're operating inside an activated virtual environment, pip automatically knows it should manage packages for that environment. Initially, the virtual environment contains only the Python standard library and a couple of utilities, including pip itself, but we can use pip to install the third-party packages that we're going to use on the project. When we looked at pip, we learned about its -- user command line option, which installs the package into a personal package library instead of the system library. That's never necessary when installing into a virtual environment because the virtual environment has changed where the default installation location is. Now that everything's set up, we can begin work. We shouldn't delete any of the files or folders created by them or pip. But other than that, we're free to create files and folders as needed for our project. It is often useful to create a subdirectory to contain our working code. In this video, we learned how to use the simple but useful them tool to isolate our coding projects from each other and from most changes to our development system. Now that we've seen all that, we're going to take a closer look at docstrings. In the next video, we'll learn how to structure our docstrings for maximum utility, how to add rich text formatting to them, and how to export them into hyperlinked HTML documentation for viewing in a web browser. Welcome back. In the previous video, we learned about the them tool and the isolated virtual environments it creates. In this video, we will take a look at how to format docstrings for maximum readability and how to transform them into structured and formatted documentation. PEP 257 documents the expectations of Python programmers and tools with respect to docstrings. The basic rules are quite simple. Use triple quotes to delimit the docstring. Triple quotes are how Python expresses the idea of a multi-line text string. The closing triple quotes should be on a line of its own if your docstring is longer than one line. The first line should present a short description of the thing being documented, such as return the distance between points A and B. After the first line, we can either end the docstring or insert a blank line, followed by a more in-depth description of the documented object, containing descriptions of parameters, attributes, usage semantics, examples, and so on. The reason for this layout is that many tools show the first line of the docstring as a pop-up, tooltip, or otherwise present it as a quick reference. The text after the blank line is presented when detailed documentation is requested. The docstring processing tools are smart about indentation, so it's safe and encouraged to indent our docstrings so that they match up with the rest of the code block that they're describing. Those basic rules are all that are required to make our docstrings interact well with Python's PyDoc and help tools with IDEs and so on, but they don't give us any way of creating well-formatted standalone documentation. That's where Sphinx comes into play. Sphinx is a tool that can process Python source code and standalone documentation files and generate nicely formatted documentation in a number of formats, notably including HTML. Sphinx, like other Python documentation tools, recognizes a markup language called restructured text, which is intentionally readable and informative, even when its markup presented as plain text rather than being interpreted. Restructured text documents are still readable in a simple text editor, but when we feed them through a tool like Sphinx, they make the end result richer. Restructured text syntax is based on the conventions that developed on the internet before actual rich text was widely available in email and real-time chat. So, for example, words are emphasized by putting an asterisk at each end, and emphasized further by making that into 2 asterisks. Paragraphs are marked by placing a blank line between them. Their syntax for list, headings, and so on, all plainly readable in text mode. The syntax is nicely described in the Python Developer's Guide, but we're going to concentrate on a few bits of markup that do a lot to enhance the documentation for our modules and packages. We've actually already mentioned one of those bits of markup When our doc strings make reference to a local variable, such as a function parameter, that reference should be enclosed in asterisks to emphasize it and make it distinct from the normal text of the documentation. The names of modules, classes, functions, methods, attributes, exceptions, global variables, and constants should all be marked properly so that the Sphinx can cross-reference them and create links to their documentation. All of these object types share a similar syntax, which is that we put a type identifying keyword between colons immediately followed by the name of the object in back quotes. As you see in this example with classes and methods, the keywords are mod for modules, class for classes, func for functions, meth for methods, attr for attributes, data for variables, and const for constants. That's enough restructured text syntax to make a big difference in the quality of our documentation. So we're going to leave it there and move on to talking about how to actually use the Sphinx tool. If it's not already installed, we can install it using pip. Sphinx can do a lot, so it's worth working through the tutorial on sphinx-doc.org. It's quite nice. For our own purposes, though, all we're interested in is turning doc strings into HTML, so we'll work through that process here. We're going to generate HTML documentation for our example package, which is just a docstring example. We start by going to the directory that contains our package directory. Once there, we run sphinx-quickstart to set things up. The first thing that sphinx-quickstart asks is what root path for the documentation should be. I find that it works well to use a folder called docs for this. So I suggest typing in docs here. Sphinx-quickstart will ask several more questions, which we can answer as we like. And then eventually it will ask if we want to enable the AutoDoc plugin. We do. The rest of the questions are not so important for our purposes. Once Sphinx-quickstart has completed, we'll want to run Sphinx-API docs to automatically generate Sphinx source files describing our package. Our doc strings are extracted and incorporated into these source files. Finally, when we want to generate the HTML, we can construct it by running make HTML from the command line. Sphinx will translate its source files, including the ones automatically generated by Sphinx-API doc, into HTML and store the result in the build directory that we specified when we were going through Sphinx-quickstart's questions. If we edit our source code and want to update the HTML documentation, we can usually do it simply by running make HTML again. If we've made major changes to the packet structure, we'll need to run Sphinx-API doc again as well. So, Sphinx can be used as a documentation compiler, which turns our docstring source code into HTML compiled code. In this video, we learned how to format our doc strings to take advantage of automated tools, such as IDEs and the Sphinx documentation compiler. In the next video, we're going to look at one more cool advantage we can get from doc strings by actually executing the examples we include in our documentation and making sure they agree with what the code actually does. Hi, in the previous video, we looked at formatting our doc strings for use with documentation tools. In this video, we're going to look at how to make examples in the documentation testable so that the documentation is never out of date. It's common to include examples of use in our doc strings, but if we're not careful, those examples can get left behind when the code changes, and wrong documentation is worse than no documentation. Fortunately, we have a tool that could check whether the documentation agrees with the code by running the examples from our documentation and seeing what happens. That tool is called doctest. To enable doctest to recognize our examples as things it could test, all we have to do is include the Python interactive shell prompt into our example. In the simplest and most common case, that just means putting a triple greater than symbol in front of each statement. For multi-line statements, we prefix the continuation line with a triple dot symbol. After each statement, we should write down the expected result of the statement, written the same way the interactive shell would write it. In other words, if we copy and paste directly from the interactive shell, we've created an example that doctest can recognize. So, writing doctest is pretty straightforward. There's a decent chance of writing a doctest into our docstrings even if we didn't know the doctest tool exists. As an added bonus, Sphinx recognizes doctests and formats them appropriately too. So, if we're going to include code examples in our docstrings, this is the way to do it. It's easy to have doctest run all the examples in a file and report back whether they worked. We just run the doctest utility from the command line and tell it which file we're interested in. The -v option makes it print out extra information, which isn't necessary, but often is helpful. All we see in this example is lack of error messages rather than any confirmation that everything worked or is tested. There are other ways of running doctest, including a Sphinx plugin that Sphinx Quick Start asks us whether we want. It's also possible to integrate doctests into a test suite. For Python's standard unit test library, or to use an integrated test runner called nose to find and execute them. Doctest directly will do, for our purposes here though. Now what happens if a doctest fails, but after looking at it, we see that the documentation and example are actually correct? Well, that means our code is incorrect. Believe it or not, this is a very good thing. I don't mean that having an error is a good thing, but that error was there, whether we found it or not. Finding it and having a test on hand that will let us check whether we've succeeded in fixing it though, that's good. So, doctest ties our code and documentation together so that they stay synchronized and serve to double check each other. That's a very useful docstring trick. In this video, we learned about writing examples into our documentation and how to use the doctest tool to check whether the examples in code are synchronized. In the earlier videos of this section, we learned about writing readable code, version control to keep track of our code, and virtual environments to keep our development projects isolated. In the next section, we'll get to learn how to turn a package into a program that can be run from the command line. Hi, and welcome. In the last section, we visited some best practices which would help us in the long run when using Python. In this section, we're going to look at how to make Python command line programs and some features that make such programs easier and more useful. In this video, we're going to look at how to create an entry point for code execution in a package and see how to run the package as a program. In previous videos, we've run command line tools like doctest and venv, venv, by typing in Python -m followed by the name of the tool we wanted to run. What were we actually asking Python to do when we did that? The -m command line switch for Python tells it to run a module. It uses the same mechanism to find the module that it would if we'd used an import statement with the module's name, and then it executes it. But venv isn't a module, it's a package. So what's happening when we do Python -m venv? We gave Python a package name, but we didn't give it a module name inside the package that it should run. When that happens, Python looks for a module named __main __ in the package and runs that. So Python -m venv means the same thing as python-mvm dot _ main _. Any module that's meant to contain a program's entry point has a problem, because simply importing the module will run the code too. That could be annoying or troublesome at the best of times, but it becomes unacceptable when we're using tools such as Sphinx or DocTest that need to import modules in order to do their jobs, but which really shouldn't actually run the module code as a program. Fortunately, there's an easy fix, because the Python interpreter itself knows which module it was told to start running and marks it as such. All modules are automatically given a variable called __main name __, which contains the module's name except the program entry point. The program entry point is always given the name __main __, even if its file name is something entirely different. So we could check whether our code was the program entry point by checking if __ equals name __ equals __ main __. If it does, we should run the program. If it doesn't, we were imported normally as code and should not run the program as main code. This even distinguishes between importing a package's __ main __ module and running it, because when we import it, the name variable contains package name __ main __, not just __ main __. In the videos in this section, we're going to work through the process of building a complete utility program called Pipeline. Pipeline will be a text mode program that can be configured to run a sequence of other programs and feed data from each program into the next. In each video, we'll apply what we've talked about to developing Pipeline further. So far, we've talked about in this section is how to make the program able to be run from Python-m, but we've seen in previous sections how to create a virtual environment to work in, and how to create a package, and how to lay out the code in the package's modules for readability. So let's put those lessons to use. Create a folder within the virtual environment to be the package and call it Pipeline. Inside the package folder, place an __ init _ .py file, which can be empty, and a __ main _ .py file. For now, the contents of the __ main _ .py file can be very simple. Just a doc string for the module, a function that should be called if the module is the program entry point, and the if statement that decides whether or not to call the launch function. The launch function doesn't have a doc string, which is allowed because it's marked as non-public by having an underscore as the first letter of its name. The launch function also doesn't do anything interesting yet. It just uses the print function to tell us that it was successfully executed. Let's run it so we can see for ourselves. Open a command line, go to the virtual environment where we created the package, and activate the virtual environment. Then type Python -m pipeline. We should see the message print out, and then the program will end. Excellent! In this video, we've seen how to add a program entry point to a package, making the package executable as a program via the Python-m command line switch. In the next video, we'll look at how to easily handle reading data from our program's command line arguments. In the previous video, we saw how to make out package execute as a program. In this video, we're going to see how to make the program read data from its command line, a common feature for programs of all sorts. Most command line programs, and a surprising number of graphical user interface programs as well, can be given extra information on the command line after the command that invokes the program. These extra bits of information are referred to as arguments, and they are delivered to Python programs as a list of strings. It turns out that there's quite a lot of code involved in turning an argument list into useful information. especially when we want to make the program as convenient for our users as possible. Fortunately, a lot of that code can be the same from program to program, and the Python standard library's argparse module takes care of much of the effort for us. The primary component of the argparse module is the argument parser class. In the minimal case, it only takes 3 lines of code to use argparse. We need to import it, create an argument parser instance, and call that instance's parse_args function. As usual with minimal cases, that's not very useful. The only arguments that the program would respond to are -h or --help, either of which would print out an automatically generated how to use this program message and then exit the program. The first thing we could do to make the argument parser more useful is to provide a value for the description parameter of its constructor. Argument parser's automatically generated help message will explain all the arguments that the program expects, but it doesn't say anything about what the program is actually supposed to do unless we provide a description ourselves. The next way we can improve the argument parser's behavior is by telling it the name of the program. If we don't provide a name, it will do its best to make a reasonable guess, but we're better off telling it ourselves. I consider the python-m command to be the canonical name for my own programs, so that's what we'll use in our examples. We set the name by passing it as a string to the argument parser constructor's prog parameter. Those changes make the programs help output prettier and more useful, but they don't actually give the program any new capabilities. We need to start adding argument specifications to the parser so we could check for them in the argument list. We do that by calling the argument parser instances add_argument method. Argparse recognizes 2 kinds of arguments, optional arguments and positional arguments. As the name implies, optional arguments are not required, but if the user chooses to include them, they have meaning. Positional arguments, on the other hand, are required by default, although we can modify that behavior. Optional arguments have names that start with the dash character. It can have more than one alternate name for the same argument. The names are passed as parameters to the add_argument method. As in this example where -p and --print are alternate names for the same optional argument. There are a lot of ways of configuring an argument when we add it to the parser, which are detailed in the argparse documentation in the library reference on docs.python.org. For options like our print example, though, the important configuration items are the action and the default. The action tells argparse what to do when it binds the argument on the command line, and the default tells it what to do when it doesn't find the argument on the command line. The action parameter can either be a string containing the name of one of the well-known actions, like store_true, or it could be a subclass of the argparse.action class. The default can be any arbitrary value, which will be stored as the value of the argument if it's missing when we actually ask the parser to parse out the argument values. The other kind of argument has to have just one name, and it can't start with a dash character. By default, these arguments collect one word that isn't part of an optional argument from the command line, in the order that they were added to the parser. If we configure the argument using the nargs option, we could change the number of words that the argument collects. If we set nargs to a number, that many words will be collected for the argument. We can also set nargs to star to mean any number of words, or plus to mean at least one word. There are a few other variables, other values, we could set nargs to, but we won't talk about them here. Let's look back at our pipeline program. I think we wanted to understand 2 arguments, an optional argument that tells it to keep going, even if one of the programs returns an error code, and a file name, where it should load and store a pipeline configuration. After the call to parse_args, we have an object named args, what contains a keep_going attribute set to either true or false, and a file name attribute containing a string. Notice that the attribute of the argument's object is keep_going, not keep-going. Python doesn't allow dash characters inside of attribute names. And argparse is smart enough to fix that for us automatically. If we wanted to set the name of the argument object attribute manually, we could have passed the name we wanted to, the add_argument method, as its best parameter. Now that we've worked out how to read the information that's given to us when the program starts, in the next video, we're going to look at how to interact with the user while the program is running. In the previous video, we saw how to get information from the user on the command line. But what do we do when we need a more dynamic form of interaction? In this video, we will look at some of Python's tools for sending information to the user and requesting information from the user. The fundamentals of interactivity are simple. We need to be able to tell the user things, and we need the user to be able to tell us things. In service of those two goals, Python provides the built-in functions print and input. Print takes any number of Python objects as parameters and prints them on the screen. Input takes a string prompt as its parameter, prints it out, then reads text until the user hits enter, and returns what the user typed as a string. That's about as simple as interactivity can get. Print and input functions can do a lot, but there are a couple of corner cases where they don't work so well. One of those is when we want the user to type in a password. If we used input to read the password, it would be displayed on the screen for anybody to read. The getPass package contains a function also called getPass, which works just like input, except that it doesn't show the text that the user types. The other corner case I want to mention is that although print can print out any Python object, it doesn't do a good job presenting complex data structures. The pprint function from the package of the same name makes complex data structures much more readable. If we want to display a list of dictionaries, pprint will do a better job of it than print would. Between those four functions, there's a wide range of user interfaces we could make, but they're pretty basic tools. We'd be reinventing a lot of wheels and wasting time. Fortunately, thanks to Python's batteries included philosophy, we don't have to do that. Instead, we'll use the standard library's CMD package to quickly build our user interface. All we have to do is inherit from the CMD class and define the methods which implement commands the user can type. We set the prompt attribute to a string that will be used to prompt the user for a command. Then we create an instance of our interface class and call its CMD loop method. Presto! Instant interface. In the example we just saw, the CMD class takes care of displaying prompts, reading in commands, and invoking the correct methods. But that's all it does. We still needed the print function if we wanted to display data from inside of a command handler method. The CMD class isn't exclusive. It does a lot of work for us, but we could still use print and input directly if we need to. That's very nearly everything there is to say about text mode interactivity in Python, at least if we want our programs to be portable across platforms. There is another standard library module called curses, which enables much more sophisticated text mode operations. But as the cursors module is not portable to Windows, we're not going to go into in detail here. Instead, let's look at defining the user interface for our pipeline program. It seems like we'd want to be able to add programs to the pipeline and manipulate the data passing between the programs in various ways. We'll also want to be able to save the pipeline when we're happy with it, and to be able to actually run it. Finally, we'll want to be able to quit the program. A help command would also be helpful, but lucky us, the CMD class will provide that automatically by using the docstrings for the command handler functions. We're just going to stub in the command handlers here because we're focusing on the interface implementation for now. So there we have a pretty decent user interface with very little work on our part. That's it for text mode interaction. In the next video, we'll look at how to actually run other programs from inside our code. In the previous video, we constructed a user interface for our pipeline program and learned about several of Python's text mode tools along the way. In this video, we will learn how to execute and control other programs from within our own, allowing us to create the heart of our example program. This ability is often useful for all sorts of system automation tasks. Making other programs run used to be something of a mess. There were different mechanisms that worked on different platforms. There were mechanisms that were convenient, and there were different mechanisms that were secure. Fortunately, that all changed in Python version 2.4 with the introduction of the sub-process module, which abstracts away the differences between platforms and makes the more secure paradigms easy to use. There are 6 objects in the sub-process package that are of particular interest. 3 of them are the call, check call, and check output functions, which are 3 variants on the same basic idea. They run a program, wait for it to terminate, and then tell us something about what the program did. The call function returns the program's exit code, which is an integer that has a program defined. Defined meaning, which is usually used to know whether the program has succeeded or failed. The check call function raises an exception if the program's exit code is non-zero, which by convention means that it exited with an error. The check output function returns whatever text the program printed and raises an exception if the program exited with a non-zero exit code. The raised exception has an attribute called output that contains the text output of the program, so even if the program exited with an error code, we could still get the output if we want it. The run function, which is new in version 3.5 of Python, is similar to the call function we were looking at just a moment ago. In fact, it is capable of doing anything that anyone would do in combination. However, being new to 3.5, it is not necessarily possible to use it in other projects, at least not yet. The 3 call functions and the run function are invoked in largely the same way. Each of them is passed a list containing the program name and its arguments. We see the output of this function ls-l on the screen. That wasn't from the call because ls-l prints something out when it runs. The exit code returns 0 though. That becomes your call. If you wanted to take that printout from the ls program and use it in our program, we need to capture. The check output function has a noteworthy keyword-only parameter called universal_newlines, which defaults to false. If we set to universal newlines to true, the text output of the program is decoded into Unicode characters using the system's default text code C codec, and newline characters are normalized. If we leave universal_newlines at its default value of false, the program output is returned as bytes, and it's up to us to do any decoding and to deal with whatever sequence of characters the current system considers to be a new line character. In this case here, we did set it to true and then split it on the \n, which is the standard new line character, and that gave us back a list of the lines that are output from the program. If we want to get fancier with our running of other programs, we'll want to use instances of the popen class, the fourth interesting thing in the subprocess package, and which allows us a great deal of flexibility and control over the execution of other programs. At the cost of a bit more complexity, the popen constructor accepts the same list of program and command line arguments that the call functions do, and a very large number of optional keyword arguments, including universal _ new lines. We're going to focus on a particular use of popen that is useful, but goes beyond what we can achieve using one of the call functions. We're going to see how to run a program in the background, while our own code is also running and send and receive data between the two programs. To manage that, we're going to need the last of our 6 interesting things in the subprocess package, the pipe constant. The pipe constant is used in conjunction with the standard in, standard out, or standard error, standard keyword parameters of popen constructor. Those parameters represent the other program's textual input, output, and error reporting. And any of them that we set to pipe are redirected to our program. In this example, we're redirecting the program's input and output to ourselves, which gives us a bidirectional data channel with the other program. So now you see we are interacting programmatically with the code on screen. That was at the beginning of this example. But since it sets in a loop, inputs and then outputs accord, and whatever it input. Once we have the pipe set up, we can send data to the other program by calling the write method on the popen object's standard in attribute. And we could read data by calling the read method or its relatives on the popen object's standard out attribute. In spite of disabling buffering with the buff size equals 0 parameter to the popen constructor, it's usually a good idea to call the flush method on standard in after writing to it, and on standard out before reading from it. We could keep on sending and receiving data for as long as both programs are running, but if the time comes when we're done interacting and just want to wait for the other program to terminate, we could call the popen object's wait method to do that. The wait method will return the execode of the other program once it's done running. A lot of the complexity of working with piped standard in and standard out is wrapped up in the popen class's communicate method, which accepts the input as a parameter and returns the output. Communicate is simple, but somewhat limited. Communication is simple, but somewhat limited because it can only be called once for each popen object and doesn't return until the other program finishes. That isn't any good for two programs that need to talk back and forth to each other. But it should be just perfect for our pipeline program, where each program receives the output of the previous program as its input. We're going to create a bunch of classes to represent the different kinds of steps in the pipeline and integrate those classes into the interface as well. Once we've done that, the program is functional, although there's plenty of room for improvement. Our particular interest is the exec step class on the top right of the screen right now, which uses popen to actually execute a program and break free of the output. We've got our example program working now, so we're going to move on to the last topic in the section, setting up a shell script or batch file to launch the program. Hi, in the previous video we saw how to make our programs run other programs. In this video, we're going to wrap up this section's example program by seeing how to make it simple to launch. We can run our program using Python-m as long as it's installed in the system Python path, or we've activated the virtual environment containing it. But once the program's solid, we really just want to be able to type its name or double-click on it and have it run. One convenient way to do that is to use a shell script or batch file. On Unix-style operating systems, including Mac OS, a shell script is a text file that starts with #bang /bin/sh and has been marked as executable. On Windows, a batch file is a file whose name ends in .bat. Both shell scripts and batch files are text files containing a sequence of command line commands, one on each line. When we type the name of the script or batch file, those commands are executed one after the other, as if we typed them all into the command line. Similarly, if we trigger the script or batch file through a graphical user interface, the commands are still executed as if we typed them into a command line, one by one. For our purposes here, that means we can put whatever sequence of commands is necessary to launch a program into a shell script or batch file. After that, we could treat that script as if it were the program itself. That's all there is to the simple case. That's all there is to the simple case. Shell scripts are capable of representing a lot more complexity, but Python is a better tool for that. So, the simple case is all we really need. In this video, we saw how to make our Python programs as simple to launch as any other program from the GUI or the command line. In the earlier videos of this section, we learned about how to make our Python packages into programs, get data from the command line, interact with the user, and run other programs as sub-processes. In the next section, we'll look at how to use parallel processing to take advantage of computers with multiple processors or cores. Hi, and welcome to our section on parallel processing. In the previous section, we created a text mode utility program and learned about several of Python's built-in packages. In this section, we're going to see how to use both the high-level concurrent.features package and the lower-level multiprocessing package to help us write parallel programs. Both are part of the Python standard library. In this video, we're focusing on concurrent.features, the more abstract and easier to use of the two packages. Our focus will be on the four main operations in concurrent features. We will then move on to the usage of future objects and end with the implications of the mechanism of data transfer between processes. Let's jump right in. Some programs are what we call CPU bound, which means that the primary factor which determines how long the program takes to complete its tasks is how fast the computer can run through its instructions. Interestingly, most programs that we use on a daily basis are not CPU bound. However, for those that are, we can often speed them up by breaking them into separate processes. On the screen right now on the left, we have a CPU-bound program. It has many things to do, represented by circles, and the speed of execution depends on how quickly the CPU can process. On the right, we have a program that is not CPU-bound, which means, most of the time, it is waiting for the execution. The processes can run simultaneously on different CPU cores, or even on completely separate CPUs. This has the net effect of increasing the number of program instructors executed per second, which means that CPU-bound programs run faster. In some programming languages, we could see the same benefit by running multiple threads for a single program. However, as I mentioned before, most programs are not CPU-bound, so the creators of Python have chosen to optimize Python's threading system for the common case. which has the side effect of making Python threads not very useful for improving the speed of CPU-bound programs. Besides, it's easier for the operating system to optimize the execution of multiple processes than multiple threads within a process. So even if threading were a viable option, multiple processes would be a better choice for a CPU-bound program. We've already seen one very low-level approach to launching a process and communicating with it in our discussion of the sub-process module. However, for cases where the reason we want to do that is because our program is broken up into a bunch of cooperative processes that work together, Python provides us with a couple of higher-level toolkits that make things easier. The more abstract of Python's parallel processing toolkits is called concurrent.futures. The concurrent.futures module is designed for programs that can be structured with one controlling process and several worker processes, where the controlling process hands out jobs to worker processes and then collects and collates the results. That's a fairly generic model, especially for CPU-bound programs. So, concurrent.futures is as widely applicable as it is simple to use. And it is simple. The basic usage is to just import it, create a process pool executor object, and then call that object's map, or submit methods to send work to the worker processes. When we're completely done with the process pool executor, and we know we'll never need it again, we call its shutdown method, or allow the with statement to do it for us. The process pool executor will take care of all the twitchy little details of creating and communicating with the worker processes. When we call process pool executors, map, or submit methods, we're asking it to call a function with the given parameters. But we want that function call to happen inside a worker process. That has some implications that might not be obvious. First of all, it means that the function and its parameters need to be pickable, which is another way of saying that Python needs to know how to turn them into a byte string that it can send to the worker process. For functions, that basically means any function is okay unless it was defined within the body of another function. For the parameters, it means that most objects will work, but generators and a few other kinds of special object can't be passed. It's important to be aware that both the function and the parameters passed to it can easily bring along information we didn't intend to send when they get pickled for communication to the worker processes. If any of the objects we send to the process pool executor references other objects, those objects get pickled up and sent to. It's entirely possible to end up sending most of the state of our program. That's particularly worth noting when the function we're asking to run is a method of an object. If the function is a method of an object, the whole object will get pickled and sent to the worker process, which means that the function call will be happening with a copy of the original object as its self-parameter, not the original object. Second, the return value of the function is pickled and returned to the controlling process. All of the warnings about passing parameters to the called function apply to the return value too. So for example, the function can't return a generator object, and if the return value contains references to a bunch of objects, copies of them will end up being sent to the controlling process. Third, and finally, the concurrent futures code that's running in the worker processes needs to be able to import the modules that our original code was loaded from. That means that we may need to use the if name equals main trick to keep the worker processes from getting stuck running complete copies of our program, when all they wanted to do was import the module and find the function we were asking to have run. We've already seen the map method of process pool executor in our example, but let's look a little closer. The map method takes a function as its first parameter. We can also pass it one or more iterables, which will be used to figure out the parameters for each call to the function. So if we ask the pool to map the foo function to the lists 1, 2, 3, and 4, 5, 6, The result is that foo will be called with 1 and 4 as its parameter, called again with 2 and 5 as its parameters, and called a third time with 3 and 6 as its parameters. There's no guarantee about which order those 3 calls will happen in, though. After all, they're likely to each run in different processes, and the relationship between process scheduling and wall clock time is partly dependent on unpredictable factors. The map method hides that fact by waiting for all the calls to finish and produce the results, then returning an iterator over those results in the proper order. Sometimes the map method is too simple. What if we want to handle the results as each worker produces them instead of waiting for all the workers to get done? What if we decide not to run the function after all? What if we want to run different functions in worker processes at the same time? For that matter, what if we want to pass keyword arguments to the function? We could do all that and more using the submit method. Each call to submit translates to a single call to the function that we pass as submit's first parameter. The rest of the parameters and keyword arguments we pass to submit are passed into the function after being sent to a worker process. So for each time we call submit, one worker process calls one function with one set of parameters. Submit does not wait for the worker process to finish running the function before returning. In fact, it doesn't even wait for the worker process to start running the function. And so, submit does not return the result of the called function. Instead, it returns a future object. Future object is in some sense an IOU for the result of the function. If we have a future object, we can use it to check whether the worker process has finished running the function to get the result returned by the function, or even to set up a callback that will be called when the function finally does finish running. We can even use the future object to remove the function call from the queue of jobs that should be shared out to the workers. The done and result methods of a future are the ones we'll use most often. The done method returns true if the job is done and false if it's not. A job is done if it was canceled, if it raised an exception, or if the job function has returned. The result method returns the return value of the job function if it completed successfully. If the job function raised an exception instead of returning a value, the worker process will catch the exception and hand it back to the controlling process as the result of the job. In this case, calling the result method will re-raise the exception so it can be handled properly. If we call the result method before the job function is done, the result method will wait for the job to complete before it returns. That can be very useful, but sometimes we don't want to wait indefinitely. If the job isn't done quickly, we want to go on and do something else for a while. In that case, all we have to do is pass the number of seconds we're willing to wait to the timeout parameter of the result method. If the timeout expires without a result being produced, a timeout error will be raised. There are a pair of functions in the concurrent.futures package that let us wait on several futures at once. They're called wait and as completed. The wait function waits until all of the futures are ready to deliver their results, or until a timeout expires. Then it returns a set of futures that are done and a set of futures that aren't. In contrast, the asCompleted function returns an iterator that produces futures one by one as they become ready to produce their results. In rare cases, the done and result methods of future and the wait and asCompleted functions of the concurrent futures package aren't sufficient to let a program process futures at the proper times. For those occasions, it's possible to have the future call a function when the result becomes available. We can do that by passing a function into the future's addDone callback method. The future will remember that function, and when the job function is done, the callback function will be called with the future object as its only parameter. The code in the callback function can then call the future's result method to get the return value or exception that the job produced. Take note that the callback function will always be called in the controlling process, but it might not be called in the same thread as the main part of the program. When we use add_done callback, we need to be careful of thread synchronization issues, which is a big reason to prefer wait or as completed when possible. Future objects also have a cancel method, which tries to tell the system that we don't want the call to happen after all. This is not guaranteed to work because if a work or process has already begun a job, that job is no longer cancelable. If the job connected to a future can't be canceled, the cancel method returns false. If the cancellation succeeded, the cancel method returns true. The concurrent futures module is perfectly suited to farming out computational tasks to multiple processes to take advantage of the CPU power of multi-core and multi-processor computers. The map, submit, wait, and as completed functions are usually all you need for that kind of task. If the program we need doesn't fit into the send out jobs and collect the results model, we're probably better off working at a somewhat lower level of abstraction. Multiprocessing module, which is the topic of the next video. Hi, in the previous video, we saw the concurrent futures package, which makes it very simple to farm out computational jobs to worker processes. In this video, we're going to look at another package that helps us handle multi-process programs that don't fit that model. But the pieces are only partly independent of each other. From time to time, they need to pass information between themselves, not just back to the controlling process. We can't do that with concurrent futures because it just doesn't fit into the model concurrent futures uses to describe parallel processing. Or what if we need to be able to cancel a job after a worker process has started running it? Again, that doesn't fit the concurrent futures model. The concurrent futures model is powerful, but its power is based in simplicity. And so, it's not too hard to imagine scenarios it can't handle. When we need to build our own model of how parallel processing should work, we can use the multiprocessing module as the foundation. The multiprocessing module contains a class called process that represents the ability to run code in a separate process. Probably the simplest way to use the process class is to subclass it and override the run method, which is the entry point for code in the other process. In this example, we've created a specific kind of process that calculates some square numbers. Then we created an instance and started it running. When we called start, the multiprocessing module did the necessary work to make sure that the run method was executed in a new process. By the way, all of the warning we discussed in the concurrent.futures video about pickling and importing modules applies to the multiprocessing module as well. When it comes to moving data between processes and importing code, they work in the same way. So far, we haven't seen anything that we couldn't do better with concurrent futures, but that changes when we start using queues, pipes, and managers. Let's have a quick overview of each, and then we'll look at them in detail. Queues are communication channels that are appropriate for one-to-any, any-to-one, and any-to-any communications between cooperating processes. Depending on how they're used, that makes them ideal for posting tasks to a worker process when we don't care which worker ends up doing the task, and for collecting the results of multiple worker processes. Any process can put a pickable object into a queue, and any process can remove the next available object from the queue. Queues are first-in, first-out data structures, which means that objects are removed from the queue in the same order that they're added. The joinable queue class adds a method which allows a process to wait until the queue has been emptied by other processes. Pipes are one-to-one communication channels. When we call pipe, we get back a pair of objects that each serve as one end of the communication stream. If we give one end each to a pair of processes, they can send messages and data back and forth through the pipe. It's usually best to have queues and pipes as the only connection between processes, because that usually maximizes the ability of the processes to work in parallel. If it's possible to organize a parallel program that way, it should be. If we find that we need to share some variables between several processes, though, we can do it using a manager object. A manager represents a special process with only one job, keeping track of the variables that other processes need. Accessing variables stored in a manager is much slower than accessing a process's local variables, and it could lead to situations where processes trying to access variables at the same time slow each other down. On the other hand, if we actually need shared variables, at least the manager handles them correctly and as efficiently as possible. Okay, let's take a closer look at queue objects. There are three methods that are primarily useful: put, get, and get under bar no wait. When we call put, an object is placed at the back of the queue. When we call get, an object is removed from the queue and returned, unless the queue is empty. If the queue is empty, the process that called get waits until it is able to remove and return an object, which will happen after some other process puts an object into the queue. When we call get no wait, on the other hand, it either removes and returns the object at the front of the queue, or it raises a queue.empty exception. Finally, we could pass a timeout parameter to the get method, in which case it will either remove and return an object within that many seconds, or raise queue.empty. We could pass queue objects around between processes by making them part of the process's initial data, or by sending them through pre-existing queues or pipes, or even by storing them in a manager. Queues are designed to be shared between processes. Moving on, let's look at pipes. Each end of the pipe has the same methods. The interesting methods are send, receive, and pull. The send method accepts object as its parameter and sends it to the other endpoint. The receive method waits for something to be sent from the other endpoint, then returns it. The pull method returns true if there's an object waiting to be received and false if there is not. The pull method can accept a timeout parameter. If we give it a number for the timeout and there's not currently anything waited to be received, the pull function will wait for up to that many seconds for data to arrive, and then return true. If no data arrives before the timeout expires, the pull method will return false. If we pass none as the pull method's timeout parameter, it will wait until data arrives before returning, no matter how long it takes. Like queue objects, pipe endpoints can be sent to other processes as they're launched, or through other queues, pipes, and so on after the process is running. Let's look at manager in more detail. Now, managers can handle many types of data, but we're going to focus on their ability to store dictionaries, lists, and namespaces. Normally, when we send an object to another process, the other process actually gets a copy of that object, which means if the other process changes the object it receives, we don't see those changes in the original process. A manager lets us create objects that behave more like queues, in that if we send the object to another process, and that process changes the object, we do see the changes in the original process, or any other process that has access to the object. The manager dict and list methods create special dictionaries or lists that can be shared between processes. The namespace method, which does indeed start with a capital N, creates a more generic shared object on which we can set attributes to share them between processes. When we have shared data that are being accessed by multiple streams of execution, which is exactly what Manager provides, we have to be careful to keep the data access synchronized. To help with that, managers can also create some standard synchronization primitives, such as locks, events, conditions, and semaphores. Lock objects are the simplest of the synchronization tools. They have a pair of methods called acquire and release. After a process calls acquire, any other process that calls acquire is forced to wait until the first process calls release. Then the acquire call in one of the waiting processes returns. allowing that process to proceed. In other words, code between an acquire call and a release call can count on being the only code accessing whatever data the lock is protecting. Notice that the lock doesn't know what data it's protecting. It's up to us as programmers to define and respect that association in our own minds. Event objects allow a process to proceed immediately if a flag is true, or wait until the flag becomes true. The flag is set to false by calling the event's clear method, or true by calling its set method. When we call the wait method, it will return immediately if the flag is true, or it will pause execution until another process calls set, and then return. Event objects are useful for making a process pause until some specific thing happens. Conditions combine some of the features of lock and event objects. Like a lock, they have acquire and release methods that can be used to protect data from simultaneous access. However, a condition object also has a wait method and a notify method, which can be used to wait until some other process does something and to wake up a waiting process. Condition objects are useful for creating data structures that synchronize access to their contents and wait when they don't have any data to return. The get and put methods of the queue class could be implemented using a condition. Semaphore objects look a lot like lock objects. The difference is that where lock objects always ensure that exactly one process has acquired the lock at a given time, semaphore objects ensure that no more than a fixed number of processes can acquire it at the same time. This is useful for doing things like limiting the number of worker processes that can access the hard disk at the same time. In this video, we saw how to use the multiprocessing package to define what worker processes do and how they interact. In the earlier video of this section, we learned how to use concurrent.futures to make a particularly common multiprocess case extremely simple. So, now we know quite a lot about how to help CPU-bound programs take advantage of multi-core and multiprocessor hardware to run faster. Take advantage of multi-core and multiprocessor hardware to run faster. Most programs aren't CPU-bound though. They're I/O-bound, which means they spend most of their time waiting for input from various sources. Parallel processing doesn't help in that situation, but asynchronous I/O does. That's the topic for our next section. Hi, and welcome to our section on Python's coroutines and asynchronous processing. In our previous section, we looked at using multiple processes to increase the rate of data processing in our programs, which is great for CPU-bound programs because it allows the program to use more than one CPU. In this section, we're going to look at the inverse case, using a single CPU to handle multiple data processing tasks at once within a single process, which is great for I/O-bound programs. In this video, we're going to take a moment to examine the differences between asynchronous processing and parallel processing. We will specifically look at why multi-threading is not good for servers, cooperative scheduling, and finally, end with the coroutine syntax for Python. When we were working with the concurrent.futures module in section 6, we saw a way to make two or more streams of code run at the same time. We could create an executor object, and then, whenever we wanted to run the code in parallel, we could tell the executor to run the code. The executor would give us a future object that we could use later to get the result of the code. And it would then run the code in a separate process. Our original code kept on running in the original process. We talked about how this could improve the performance of CPU-bound programs by letting the code be divided up between multiple computer cores. But it seems like a technique that could be convenient in a lot of other circumstances. It's handy to be able to tell the computer, go do this, and let me know when you're done. One place where that ability seems particularly useful is in network server programs, where having a separate stream of execution for each connected client makes the logic and structure of the code much easier to grasp, which means it's easier to write bug-free servers when they're structured that way. There are ways to write a server that uses only a single stream of execution, but if we have a way of writing servers that probably introduces fewer bugs, why wouldn't we? The problem is resource overhead. Every process running on a computer uses up memory and CPU time, of course. But in addition to the memory and CPU time, it actually needs to run its code. The operating system also needs to expend resources to manage the process. As it happens, the time spent on switching between processes is significant. The memory overhead is enough that it becomes a limiting factor on how many clients a multiprocess server can handle simultaneously, and other internal operating system resources may be even more limiting. For CPU-bound programs, there's a sweet spot that produces optimal results, where the program has one process per CPU core. For an I/O-bound program, which most servers are, any process beyond the first are nothing but overhead. As I mentioned, there are ways to write single-process servers that can handle multiple clients at once, with much lower overhead per connected client. Using these techniques actually allows a server to handle many more clients at once than a multi-process server program could. At once, even when not operating at full capacity, a single-process server leaves more of a computer's resources available for other uses. So, on the other hand, we have a way of writing servers that is logically structured and less prone to bugs, but wastes resources. On the other hand, we have a way of writing servers that is resource efficient, but easy to get wrong. Can we somehow get the best of both worlds? The answer is yes, fortunately. Python standard asyncio module combines the low-level techniques that allow a single process to service multiple clients with a cooperative coroutine scheduler. The end result is a programming interface that looks and acts a lot like concurrent .futures, but with much lower overhead per stream of code execution. That's great, but what's a cooperative coroutine scheduler? For that matter, what's a coroutine? A coroutine is a computer science concept, a function that can be paused and resumed at certain places within it. Each time it pauses, it can send data out, and each time it is resumed, it can receive data. Python programs can define coroutines using the async and await keywords, and asyncio makes extensive use of them. A cooperative coroutine scheduler is a piece of code that picks up the execution each time a coroutine pauses and decides which coroutine should get to run next. It's called a scheduler because it keeps track of multiple streams of execution and decides which one gets to run at any given time. It's called cooperative because the scheduler can't yank the right to be running away from one coroutine and give it to another. It has to wait until the running coroutine pauses itself, and then it can select another coroutine to run. In Python coroutines, the pause and resume points are the await expressions, which are also how we call other coroutines. Every time we want to perform a function, call on a coroutine from inside another coroutine, we await the coroutine we want to call. As far as the semantics of the code work that behave just like calling a function from inside a function, the other coroutine runs until it returns, and we get back the return value. That's how the code behaves. But what it actually does is quite a bit more. The first thing that happens is that the coroutine we're running is paused. The coroutine we want to call is handed off to the scheduler, which places it into its list of coroutines that need to run. Then the scheduler checks to see whether anything has happened that a coroutine was waiting for, such as new data coming in across the network or another coroutine returning. And if so, it adds the waiting coroutines to the list as well. Then the scheduler picks one of the coroutines that needs to run and unpauses it. That means that if a coroutine has a long-running loop that doesn't contain any await expressions, not only will it block any other coroutines from running, it will also keep the program from checking for new data coming in and prevent assorted other input and output operations from being serviced. If we have such a loop and there's just no reason to call any other coroutines inside it, we can place an await async.io sleep 0 statement into the loop body, which simply gives the scheduler a chance to do its thing. That little bit of extra complexity that comes from needing await expressions is the price of cooperative scheduling. But since the payoff is efficient and logical code for I/O-bound programs, it's often worth it. That's it for this video. In the next video, we'll look at some of the nuts and bolts of working with async.io. In the previous video, we learned about Python's coroutines and some of how a cooperative coroutine scheduler works. In this video, we'll try our hand at writing some asynchronous code using Python coroutines and async.io. It's easy to create a coroutine. All we have to do is use the async keyword on a function and use await anytime we want to call other coroutines. Once we have a coroutine, though, we can't just call it. To start the ball rolling, if we try to call it, it just immediately returns a coroutine object. That's not much use. Instead, we need to add the coroutine to async.io's scheduler as a new task, and then we need the scheduler to run, arranging for coroutines to execute and handling input and output events. The async.io package automatically creates a default scheduler, also called an event loop. While it's possible to create new event loop objects or to replace the default one, for our purposes, the default event loop will work just fine. We could get a reference to it by calling async.io's getEventLoop function. To tell the scheduler that we want it to start a new task running the given coroutine, we call async.io's ensureFuture function. By default, this will create the task in the default scheduler, but we can also override that by passing an explicit event loop to the loop keyword only parameter of the ensureFuture function. Notice that we didn't just pass the coroutine function to ensureFuture. We actually invoked it right there inside ensureFuture's arguments. Just because the ensureFuture function doesn't actually want a reference to the coroutine function. EnsureFuture wants the coroutine object that we saw the coroutine function return earlier. The name EnsureFuture might seem somewhat odd. If it's used for launching tasks, why is it called that? The fact of the matter is that launching tasks is basically just a side effect of what the function conceptually does, which is wrap. Wrap its parameter in a future object, if necessary. It just so happens that a future for the return value of a coroutine would be useless if the coroutine was never scheduled to run. So, ensureFuture makes sure that it does. The ensureFuture function adds a new task to the scheduler whether it's called from normal code or within a coroutine, which means that anytime we want code to run in its own stream of execution, we can use ensureFuture to get it going. Even now that we've added the coroutine to the scheduler as a new task, nothing happens. That's because the scheduler itself is still not running. That's a problem easily solved. We just need to call either the run forever or run until complete method of the loop. Finally, our coroutine actually executes. As the names imply, run forever causes the event loop to run forever, or at least until it's explicitly stopped by calling its stop method, while the run until complete method causes the loop to keep going until a particular future object is ready to provide a value. The return value from ensureFuture is a future object, so it's easy to have the scheduler run until a particular task is done. This example runs two coroutines simultaneously as two separate tasks in the same scheduler. The coro1 coroutine contains an infinite loop, so it will never finish. But the coro2 coroutine not only finishes, it eventually calls the event loop stop method to force run forever to terminate. This example behaves exactly the same way, except it uses run until complete to automatically stop the scheduler once coro2 is finished, instead of explicitly calling stop. The code looks a little cleaner this way, so as a rule of thumb, it's probably better to only use stop when some sort of error makes it necessary to dump out of the event loop. In both of the examples we've just seen, there's a line of code to set the logging level to critical. That's because the event loop issues an error message if it is stopped while there are tasks, such as the coro1 task, still running. In this case, we know it's still running and don't care, so we suppress the message. It's usually better to arrange for all of our running tasks to exit cleanly instead of just killing them like this, which is why the error message is printed. But in this case, there's no problem, so we just keep the message from printing. Regardless of how we choose to run and stop an event loop, once we're completely finished with it, we should call its close method. That closes any open files, network sockets, and other I/O channels that the event loop is managing, and generally cleans up after it. A good way to handle that is to use the context lib.closingContext manager, which guarantees that the close method will be called once the with block ends, even in error situations. The close method should be called when we're completely done with an event loop, but that doesn't necessarily mean that it should be called right after the run forever or run until complete call finishes. The event loop is still in a valid state at that point, and it's perfectly okay to, for example, add some new tasks, start the loop running again. As you've probably noticed, an async.io event loop object fulfills basically the same role as a concurrent.futures executor object from a programming interface point of view. That's not the only similarity. In the next video, we're going to look at async.io's future class and how it's used. In the previous video, we saw how to launch the async.io event loop and scheduler and add coroutines to it as tasks to execute. In this video, we'll learn about async.io's future class and how to wait for data we don't have yet. Async.io's future objects look and behave pretty much like concurrent.futures future objects, but they're not interchangeable. They have subtle differences in behavior and, of course, major differences in how they interact with the underlying systems, which are completely different. Still, each future is a way of referencing a value that may or may not have been computed yet, and if necessary, a way of waiting for that value to become available. The most commonly used feature of a future is to wait for its value to be determined and then retrieve the value. For async.io's future objects, that is done by simply awaiting the future. That will tell the scheduler to pause the coroutine until the value of the future becomes available, after which the future's value is sent into the coroutine as the result of the await expression. If the future represents a raised exception instead of a value, that exception is re-raised from the await expression. If we don't want to wait, we could call the done method to check whether a future is ready. And if it is, we could call the result method to retrieve the value. So, the syntax and semantics are a little different, but the basic idea of a future is the same in async.io and concurrent.futures. When we're working with async.io, we use future objects in all the same places we might in concurrent.futures. There's one circumstance where even using futures doesn't make it simple to wait for data, and that's when we want to process a stream of data values as they arrive. Sure, we could loop over an iterator of future objects and wait for each of them to become ready to provide their values. But that's clumsy and suffers problems with knowing when to stop the iteration. Instead, Python provides us with an asynchronous iteration protocol, which allows us to write our fetch the next value function as a coroutine. That means that the iterator can wait for each value to arrive and simply return it. Our loop works properly and we avoid all the confusion about when to stop. Why do we need a special async for statement and a separate asynchronous iteration protocol? It's because asynchronous iteration only makes sense inside of a coroutine. Having a separate looping statement and protocol keeps us from stumbling into ambiguous situations where the computer isn't sure what we want it to do. In this video, we took a look at using a future to wait for a single value or an asynchronous iterator, which may well use futures internally, to wait for a sequence of values. In the next video, we'll be looking at synchronization and communication between asynchronous coroutine tasks. Hi again. In the previous video, we saw how to use futures and the asynchronous iteration protocol to wait for data to process. In this video, we'll take a look at more ways to share data between tasks and synchronize their operations. The async.io package provides lock, semaphore, event, and condition classes that are pretty similar to the ones we looked at in the context of concurrent.futures. They provide the same method names and fulfill the same roles. The important difference is that for async.io's versions, some of the methods are coroutines, and some are not. Specifically, in each case, the acquire and wait methods, if they exist, are coroutines that must be called by a wait. This is because they need to be able to pause until some specific thing happens. And only a coroutine can pause and hand off control to the scheduler. Having mentioned lock and the rest, I want to point out that while they are sometimes necessary, they are less often needed under async.io than they would be in concurrent.futures or other systems which provide multiple streams of execution. That's because async.io scheduling is cooperative. It's only possible to switch between execution streams at await expressions, which means that if there are no awaits within a critical section of code, it can't be interrupted. No other task can modify the same data at the same time because no other task has an opportunity to run any code during that time. Thus, lock and such are only needed when a critical section of code does in fact use await at least once. We've seen as completed and wait functions before in concurrent.futures. Async.io's versions are coroutines because they too need to suspend until it's time to continue executing. But they're not much different in how we use them. The wait coroutine still waits for a group of futures to end, with an optional timeout, and returns a list of the futures that are ready and a list of futures that are not ready when the time expires. The asCompleted function still takes a list of futures and produces futures of the results in the order that the results become available. Then we extract the actual values from the futures with await and are good to go. In this code, there's no telling what order the results will become available, but each time a value does become available, it gets printed. Async.io provides some other interesting coroutines for collecting data from futures, particularly wait for and gather. The wait for coroutine lets us wait for another coroutine to finish, but with a timeout. The first two coroutines in this example do the same thing, except that if food doesn't finish within 5 seconds, the second version will raise an async.io timeout error. In the third code block, we're still doing the same thing, except if food times out, we print a message. Then there's the gather coroutine. What it does is take a bunch of futures and make a single future that will be done when all the sub-futures are done, and result in a list of the sub-futures results. There are a bunch of uses for something like that. But one very nice thing we can do with it is use it to construct the future that we pass into run_until_complete. In effect, we're telling async IO that it should run until all of these futures are complete. Futures are great for communicating a one-off value between tasks, and event objects are good for sending simple signals. But sometimes we want a more fully featured communication channel. Fortunately, async IO provides us with a queue class and a few variants based on it. Async IO's queue has both the put and the get methods as coroutines. So, we need to call them with await. And we have to already be in a coroutine to call them, unless we were to actually use the ensure future function to launch them as separate tasks. However, the queue class also has methods called put no wait and get no wait that are not coroutines and can be called from anywhere. That makes the queue class quite useful for communicating new data into a system of coroutines, as well as sending data between coroutine tasks. Async IO provides a couple of variant queue types that return their stored values in different orders. Instances of priority queue give back the smallest object they contain, according to less than comparison, when we call get or get no wait. So if a priority queue contains 34, 2, 5, and 97, calling its get coroutine would return 2. Then next time, it would return 5, then 34, then 97. A LIFO queue, on the other hand, always gives back the most recently added object. It is, in other words, a stack data structure. Async IO also provides a joinable queue class, which adds an extra join coroutine and a method called task done. With a little bit of extra work, using a joinable queue allows coroutines to pause and wait until the queue has been emptied. In this video, we looked at tools that we can use to transmit data to and from asynchronous coroutine tasks, and force synchronization on them when necessary. In the next video, we're going to see about using async IO and coroutines to write a client-server program that communicates over the network. Hi. In the previous video, we looked at internal data communication between tasks in async IO. In this video, we'll be looking at communicating data between a client and a server using network protocols. So we've covered how async IO works and a bunch of tools that can be used to manage the execution of multiple streams of code. That's all great, but what about doing some actual IO with it? The primary motivation for people to use asynchronous IO is when writing network clients and servers, although that's certainly not the only possible use. So not only does async IO make network communications efficient, it also makes them easy. Here, we have the code for a simple client-server pair of programs. They just read and write the same few bytes over and over, but they also serve to demonstrate everything needed to communicate across the network. There should be little about the client that is mysterious. It runs only a single task, which uses async IO's high-level API to open a connection and then send and receive data through it. The server is able to handle simultaneous connections from many clients at once. Because the start server coroutine we called launches a new task to run our serve coroutine each time a client connects to the server. Each task has the job of handling a connection to a single client, so the serve coroutine is almost as simple as the client coroutine. There's a little bit of extra code to handle a connection reset error, which is the exception that gets raised if the client suddenly disconnects while the server is trying to read data from it, and a little more to handle the class where the request is an empty string, which the readline coroutine can only produce if the client has closed the connection in a less precipitous manner. In both cases, we want the server to stop worrying about that particular client, which we can do simply by returning from the client handling coroutine. the task running the coroutine finishes, and that's that. In the launch coroutine on the server, we called another coroutine called waitClosed. That pretty much does what it says. It waits for the server to be closed. Without that call, our launch coroutine would immediately terminate. And since we used run until complete, the whole program would terminate immediately afterward. That would happen because start server launches off a background task and then returns, rather than managing the server directly. And that's about it. There's a lower level communication API that Async I/O provides. But for the vast majority of cases, the lower level API is unnecessary. Async I/O makes network communications simple. In earlier videos of this section, we learned about coroutines, data exchange between coroutine tasks, and asynchronization. Now we've seen how to get a payoff from all of that by using those tools to write a network client or server. In the next section, we're going to look at various parts of Python that can be redefined within our program source code and how to use them. Hi, and welcome. In the last section, we learned about asynchronous I/O and coroutines. In this section, we're turning our attention toward metaprogramming and programmable syntax. We're going to look at various ways Python allows us to control or alter the meaning of syntactic elements and how to use those features beneficially. Metaprogramming is a blanket term for techniques where programs use program code or data structures constructed directly from program code as data to be manipulated. Python has a number of different features that can be thought of as metaprogramming, and in this video, we're going to look at one of the most ubiquitous function decorators. We'll see how to construct a decorator, how to use it, and how it works. The basic definition of a decorator is simple. It's just a function that takes another function as its input, does something with it, and then returns the result of its operations. The return value replaces the original input function, so the changes a decorator can make are potentially quite drastic. A decorator that doesn't change anything at all is a function that accepts one parameter and immediately returns it. Python has a special syntax for applying a decorator to a function using an @_ syntax. Using this syntax, we just write an @ symbol followed by an expression that evaluates to a decorator function. We put that on the line right before the definition of the function we want to decorate. This syntax means as soon as we're done defining the function, call the decorator function on it, and then assign the return value of the decorator to the variable that would have contained the function. Python includes a few decorators in the global namespace and an expanding list of them in the standard library. The most commonly used global decorator is static method, which makes a class member function be callable through the class rather than through an instance, just like static methods in other languages. It's also possible to use multiple @ lines before a def, in which case multiple decorators will be invoked. The decorator that's closest to the def will be called first. Then its return value will be passed in to the next closest decorator, and so on. Eventually, the return value of the topmost decorator will be assigned to the function's name in the containing scope. one of the most common uses for decorators. In fact, the reason they're called decorators is to add attributes to function objects. These attributes can be used by code in other parts of the program to distinguish decorated functions from each other and from undecorated functions. This is easy to do. Inside the decorator, we assign the attributes to the function just like we would for any other object, and then we return it. Then, elsewhere in our code, we could check for the attribute and respond accordingly. That's all well and good, and often quite useful, but we could do a lot more with decorators. For example, we could enclose the function in a wrapper that performs some computation before or after calling the function. To do this, we want to define the wrapper inside the decorator. If you haven't seen this before, it means exactly what it looks like. The definition of the wrapper function is actually inside of ints only. So, when ints only is called, it defines and then returns a wrapper function. Each time ints only is called, it defines a new wrapper function. When a function is defined inside another function, the containing function's local variables remain available to the inner function. In this case, the wrapper does some manipulation of the function arguments and then calls the wrapped function and returns its results. We imported and used a decorator called wraps in the last example. The wraps decorator's job is pretty straightforward. It makes the wrapper look like the wrapped function to tools like PyDoc. However, wraps took a parameter. How does that work if a decorator always accepts just one parameter? And that's the function it's being applied to. The key is that the @ symbol isn't followed by the name of a decorator per se. It's followed by an expression that evaluates to a decorator. So, wraps isn't actually a decorator. Strictly speaking, it's a function that returns a decorator. When Python evaluates the function call expression, wraps returns a decorator function, which is then applied to our wrapper. If we wanted to modify our ints only decorator so that we could specify an arbitrary function that would be applied to all the parameters, it would look like this example. So now we have a function called only, which returns a decorator, which in turn returns a wrapper, which calls the original function. That might look terribly inefficient, but in fact, the only overhead comes from invoking the wrapper each time we call the function. The outer two layers of code only run once when the function is defined. So that's how to use function decorators, and a taste of the sort of things we can use them for. In the next video, we'll look at another programmable syntax feature of Python that meshes nicely with function decorators. In the previous video, we saw how function decorators use functions as input data to manipulate. In this video, we'll take a look at how to associate metadata with functions beyond the docstrings we learned about in section 4. In the last video, one of our examples was a decorator that automatically passed all of a decorated function's arguments through an adapter. That's pretty cool, but what if we wanted each parameter to be handled differently? Sure, we could pass a whole bunch of adapters into the wrapper, but that becomes ugly and clumsy as we start dealing with functions that accept more parameters. What we'd really like to do is attach metadata directly to a function's parameters. Fortunately, that's exactly what function annotations are for. This example shows off Python's function annotation syntax. To associate a value with a parameter, we put a colon after the parameter name, and then we write an expression. That expression will be evaluated when the function is defined, and the result will be stored associated with the parameter name. We can also annotate the return value of a function by writing a -- arrow symbol after the function's parameter list, and then an expression, which will also be evaluated when the function is defined, and the result stored associated with the word return. Because return is a keyword, there's no chance that it will collide with a parameter name. All the annotations are stored in a dictionary called ~annotations. which is an attribute of the function itself. As we can see here, annotations are not type declarations, though they could certainly be used for that purpose, and they resemble the typing syntax used in some other languages. They are arbitrary expressions, which means that arbitrary values can be stored in the annotation dictionary. They don't have any meaning to Python itself, except that it should store the values. That said, defining parameter and return types is a common use of function annotations. If we find ourselves using a tool that assumes annotations are type declarations, when we want to use them for some other purpose, we can use the standard no-type check decorator to exempt our function from such processing. Normally, this isn't needed because most tools which use annotations have a way of recognizing the ones meant for them. The decorator is for protecting the corner cases, where things are ambiguous. Annotations combine well with decorators because annotation values make a good way to provide input to a decorator, and decorator-generated wrappers are a good place to put code that gives meaning to annotations. For example, let's rewrite that decorator from the previous video. We'll switch to only accepting keyword arguments, just to keep the example relatively simple. So, the adapted decorator encloses the function in a wrapper. That wrapper only accepts keyword arguments, which means that even if the original function could accept positional arguments, they have to be specified by name once the function has been wrapped. The wrapper also looks for adapters in the function's parameter annotations and applies them before passing the arguments into the real function. Once the function returns, the wrapper checks for a return value adapter and, if it finds one, applies it to the return value before finally returning. When we take to consider the implications of what's happening here, they're pretty impressive. We've actually modified what it means to pass a parameter into a function or to return a value. Let's look at another example. Sometimes one or more of a method's parameters don't require any processing except to assign them to an attribute of self. Can we use decorators and annotations to make that happen automatically? Of course we can. Let's say that if a parameter is annotated with a string, the value assigned to that parameter will be assigned to an attribute of self, using the string as the name. And if the parameter is annotated with true, the attribute will have the same name as the parameter. If there's no annotation, or if it's not a string or true, nothing should happen. Again, for simplicity's sake, let's limit ourselves to keyword arguments. As we see here, annotations simplify all sorts of code-based manipulations of code. We're using basically the same techniques as in the previous example, but we're doing something entirely different with them. We've been looking at decorators as the primary consumers of function annotations, but that's not necessarily the case. Any code which uses function objects might be written to benefit from annotations. That means anywhere where we pass a function as a callback, we could potentially use function annotation data to make the code smarter about what it does with the function. Event handlers could be annotated with the names of the values the handler wants to receive. Dependency injection could be automated in a similar way. Constraint-based systems could be provided with the constraints that apply to each parameter. Probabilistic reasoning systems could be annotated with prior probability distributions. Parameters could be annotated with the proper user interface element to display in order to have the user input that parameter's value. The possibilities seem endless. Before we wrap up this video, I'd like to point out one thing that may be helpful down the road. Our example decorators that worked with annotations were all limited to keyword arguments for simplicity. If you find yourself wanting to do similar things, but needing to handle all sorts of parameters, the inspect package's signature function will simplify that process, significantly. So, function annotations are a great way of adding metadata to functions, which can affect later handling of them in all sorts of ways. In the next video, we're going to look at class decorators and how they're similar and different from function decorators. In the previous video, we took a look at function annotations and particularly how they interact with function decorators. In this video, we'll look at class decorators, which are conceptually similar to function decorators, but open different doors. Class decorators work in the same basic way that function decorators do. A class decorator receives a class as its only parameter, and whatever it returns replaces that class. The return value doesn't have to be the same class or even a class at all, but it should be something that is meaningful when it's bound to the class's name. It's rarely useful for a decorator to return none. Also, like a function decorator, a class decorator can modify the attributes of a class or enclose the whole class in wrapper code. However, modifying the attributes of a class is effectively the same as modifying the class's source code, which means that unlike with functions, a class decorator can actually alter the structure of the decorated code, not just wrap it. Modifying class attributes is straightforward. We just use the built-in getAttribute, setAttribute, and delAttribute functions. In this example, we see a simple class decorator that makes the attributes of the decorated class readable through the square bracket syntax. And at the same time, make sure the class doesn't allow setting or deleting values through the square bracket syntax. While rewriting classes via decorators can be a powerful technique, it's not a complicated or surprising one, so there's not much more to say about it. We can also wrap up classes in their entirety. One common use for that technique is to replace a class with a factory function. Using a factory function as the interface to creating class instances lets us choose to return an existing object, if there's one we think is more appropriate than actually creating a new instance. Calling a factory function means give me the right object for these parameters, rather than give me a new object for these parameters. Let's take a look at an example class decorator that replaces the class object with a factory function for instances of that class. We'll assume that any two instances that were created with the same parameters should actually be the same object. In this example, we're using a weak value dictionary to keep track of the existing instances of the class and what parameters that were constructed with. That doesn't have anything to do with class decorators per se. Instead, we're doing it because we don't want the cache to prevent the instances from being garbage collected. That's a good practice whenever we make a factory function that keeps track of the instances it creates. Another bit of good practice that we're demonstrating here is that we've assigned the class itself as an attribute of the factory function. That means that code outside of the factory function can still access the class object if it really needs to. So let's take a look at our factory making decorator in action. Notice that the thing named unique is in fact the factory function that was created for the unique class, rather than the unique class itself. The actual class ends up being named unique.type. Also, notice that U1 and U3 are not just equal, they're actually the same object. Meanwhile, U2, which was created with different arguments, is a different object. Now we're going to take a look at something really wild. The syntax we use for defining classes is pretty generic. It could be used to represent all sorts of different data structures. So why not use class decorators to transform class definitions into objects of various types? By doing this, we can achieve a sort of sideways declarative programming paradigm. For our example, let's say we want to connect to a SQLite database and create some tables in it if they don't already exist. We can make Python's class syntax work for us as a convenient way of expressing that idea. We want the usage to look something like this, where the class structure and attributes provide the information that's needed to construct and configure a database connection for us. The end result should be a connection object, which we can use to issue queries according to the Python database API. There are a great many details that are ignored or handled simplistically by this example, but it captures the general idea. The class objects that Python creates automatically when it's evaluating these statements are used to provide structured data input to the decorator called database and then discarded. The database decorator returns an open Python database API connection object, not a class of any sort. In this video, we saw how the class decorators work exactly as function decorators do, but because they're operating on classes, the possibilities are very different. We saw how to modify classes, wrap them, or even replace those using decorators. In the next video, we'll look at a different way to programmatically modify classes using metaclasses. In the previous video, we learned about class decorators, which let us transform a class object in whatever way we choose. In this video, we'll look at metaclasses, which let us affect the creation of class objects right from the beginning. Like class decorators, metaclasses are a tool we can use to adjust the basic meaning of a class. In concept, though, they're very different. A class decorator takes an already created class and transforms it in some way. A metaclass, on the other hand, can affect how a class is created, how it behaves, and even how classes that inherit from the modified class are created and behave. To understand metaclasses, we first have to grasp the idea that classes are objects, and more than that, they are instances of another class called type. Anytime we create a new class, we're creating an instance of type, unless the class has a metaclass. If the class we're creating has a metaclass specified, or it inherits a metaclass from its ancestors, then the new class is an instance of the metaclass, rather than being a direct instance of type. That sounds like we could change the behavior of a class completely by giving it an unusual metaclass, but actually, all metaclasses have to resemble type, or Python wouldn't be able to use them properly. Most of the time, metaclasses are actually subclasses of type, which makes things simple. Alright, so what can we do with a metaclass? First of all, we can run code before the code inside the class block is evaluated. For each class, which is an instance of the metaclass, we do this by giving the metaclass a prepare method, which should be a class method or a static method because it will be called before the instance is created. The prepare method is passed the name of the new class and its list of parent classes, as well as any keyword arguments supplied by the user. The prepare method can do whatever we want it to, but it should also return a dictionary or similar object that could be used to hold the class's attributes. We can pre-assign values into the attribute dictionary from inside of prepare, so we can actually assign attributes to the class before it even exists. That brings us to the second thing that metaclasses can easily control, the class's namespace. In our last example, we returned a dict instance from prepare, so instances of this metaclass use a normal dictionary to store their attributes while their code is being evaluated. But we can return any dictionary-like object from prepare. For example, we could return an ordered dict if we wanted to keep track of the order in which attributes were created, or a default dict if we wanted all attributes to have a default value. We could even use a weak value dictionary if for some reason we wanted the class to not protect its attributes for being garbage collected while it was being evaluated. Of course, those are just dictionary-like classes that exist in the standard library. We could also return a custom dictionary-like class from prepare, which could conceivably do almost anything. If we want a class that ignores the case of attribute names while its code is being evaluated, we can do that. There's a reason why I keep saying while the code is being evaluated. After prepare is called, the code inside the class block is run, and it uses the dictionary that was returned from prepare as its namespace. But after that, the meta class's new method is called. One of the things new needs to do is to call type.new to actually allocate and initialize a chunk of memory to contain the class data. And one of the things type.new does is convert whatever we pass it as a namespace for the object into a normal dict. This means that if we want to retain special information that our namespace object knows, we need to store it somewhere where we can find it later. We can make whatever changes we want to the internals of the class. Once we've created the class object in the new method of the meta class, we can programmatically add, remove, replace, or wrap the class contents, much as we could in a class decorator. We can also return something that isn't actually a class object at all, just as we could with a class decorator. The difference, aside from a bit of extra typing, is that subclasses of a class that has a meta class will also inherit that meta class, while class decorators are not inherited. That means that using a meta class, we can make our unusual behaviors inheritable. This example makes it so that any class that descends from the class where the meta class was originally applied can find all the other classes that also descend from that ancestor. In this video, we saw how to use a meta class to affect the construction of a class object and how to make unusual behavior inheritable by making it part of a class's meta class. In the next video, we'll move to a less esoteric topic and discuss context managers. In the previous video, we looked at meta classes, what they are, and what they can be used for. In this video, we'll look at what may be Python's most used programmable semantic element, context managers. Context managers are pieces of code that plug into Python's with statement. A with statement contains a block of code, and the context manager is able to run its own code, both before and after that block is executed, with the after code guaranteed to run no matter what happens in the block. The Python standard library makes quite a lot of use of context managers. Open files can be used as context managers, which guarantees that the file will be closed at the end of the block. Lock objects can be used as context managers, in which case they acquire the lock before the block and release it when the block is finished executing. SQLite database connections can be used as context managers, allowing them to automatically commit or roll back their transaction when the block finishes. There are other examples, but we can already see how useful context managers can be. They simplify the code by combining setup and cleanup into one thing, and they improve the code by guaranteeing that the cleanup code actually gets run. So how can we write our own context managers? There are actually two ways. The simplest is to use the context lib context manager decorator on a generator function. As we see here, when we create a context manager this way, we can write it as one continuous piece of code. We can think of the yield statement as a proxy for the whole code block that the with statement contains. If that block raises an exception, it will look to our context manager code as if the yield statement raised that exception, so we can wrap it in a try statement to deal with any exceptions that might occur. We saw the as clause of the with statement when we used file opening as an example of a context manager. That lets us bind a value returned from the context manager to a variable accessible within the with block. If we yield a value from our context manager code, that value will be the one assigned through as. In this example, we yield a function that prints the word during, so the entire result of our with statement is that it prints before, during, and after in that order. We can also write context managers by adding enter and exit methods to objects. Any object that properly implements those methods can be used as a context manager, which is how objects such as open files and database connections are able to do double duty as context managers as well. Here's an example in which we create a specialized version of a dictionary which could serve as a context manager. Within the scope of the with block, we can read and write data through the object that we returned from enter. But those changes will only be applied to the main dictionary if the block exits without raising an exception. The return value of the enter method is used by the with statement for the value to assign through the as clause. So in this example, the variable trans contains a chain map instance. Chain map objects are dictionaries that can have a parent dictionary. If a looking in the chain map fails, if looking in the chain map fails, it tries looking up the same key in its parent. The exit method needs to accept parameters that specify the exception type, exception value, and trace back if an exception was raised in the with block. If no exception was raised, those parameters will all contain none. If an exception was raised, we need to decide whether and how the context manager will handle them. In our example here, we decide whether to apply the changes to the main dictionary based on whether or not an exception was raised, but otherwise ignore the exception. If we wanted Python to consider the exception to be handled, we could have returned true from the exit method. That would be functionally equivalent to catching the function with a try except statement. There's another variation of the class-based context manager, which supports asynchronous, coroutine-based context management. For the asynchronous protocol, the double bar enter, double bar and double bar exit, double bar methods are replaced by a enter and a exit coroutine methods. And the context manager is invoked by an async with statement. That small change buys us the ability to have the enter and exit methods invoke other coroutines, wait for data to come in from the network, and otherwise behave nicely in an async.io based program. In this video, we saw how context managers work and learned how to make our own for use in either synchronous or asynchronous code. In the next video, we'll look at one more way of programming the semantics of basic Python operations when we look at descriptors. Hi, in the previous video, we looked at context manager, both synchronous and asynchronous. In this video, we'll take a look at one last way altering the semantics of Python syntax using descriptors. Reading and writing variables is one of the most fundamental aspects of programming. Python's descriptors lets us alter how it works. A descriptor is an object that is stored in a class and controls what it means to get, set, and delete a specific single attribute for instances of that class. If we want that sort of control over multiple attributes, we just add a descriptor to the class for each attribute we want to control. Python's built-in property decorator provides a simple way to create a descriptor. The first prop method we wrote here tells Python how to figure out the value of an attribute called prop, which in this case just means fetching it from another attribute and printing the value. The latter two prop methods are decorated to make them into the setter and the deleter for the prop attribute, which means that assigning a value to prop actually means calling the setter method, and deleting the prop attribute actually means calling the deleter method. Both methods are optional for properties. Leaving them out makes the attribute that the property describes into a read-only attribute. Properties simplify the construction of descriptors for a common case. But there are use cases where we need a descriptor that property can't handle well. For example, what if we were planning on making a class that represented remote data and we wanted its attributes to push and pull data from the remote source? We could do that with properties, but we'd end up writing very similar code over and over as we implemented each attribute. It would be better to have a remote resource descriptor class and just add a bunch of instances to our local stub class. Let's go ahead and do that as an example. Actually, interacting with the network requires a fair amount of code, so it's a good thing we can avoid repeating it over and over. The remote resource class we've got here has get, set, and delete methods, which determine what happens when an attribute that is controlled by an instance of this class is accessed. The get method, perhaps surprisingly, takes two parameters: the instance through which the attribute is being accessed, and the class through which the attribute is being accessed. It's like that so we can handle both instance attribute access and class attribute access. When accessing a class attribute, the instance parameter is none. In our case, we just return the descriptor if somebody tries to access the attribute as a class member instead of an instance member, which is a reasonable default in a lot of cases. The set method is passed an instance and a value, and conceptually represents setting the controlled attribute of that instance to the value. Unlike get, it doesn't have support for setting a class attribute, so instance will never be none, and we don't need a class underbar parameter. The delete method is just passed an instance and represents removing the controlled attribute from that instance. Notice that none of the descriptor methods are told which attribute they represent. The assumption is that their self-parameter will specify that one way or another. In our code here, we've chosen to pass the necessary information into the descriptor's constructor and store it as an attribute of self. But in other circumstances, we might use self or self's ID as a key into a dictionary to store per instance state for the descriptor, or use the instance as a key into a dictionary stored in self. We can't just store per instance data as attributes of self though. The descriptors are attributes of the class, not the instance. So their self values are shared by all instances of the class that contains them. Once we have the remote resource class, creating classes that have remote attributes becomes easy, as demonstrated by our record class here. In this video, we saw how to create simple descriptors using the property function and more complex descriptors as classes. Either way, we can control what it means to get, set, or delete an instance attribute. In the earlier videos of this section, we saw several other ways of altering the meaning and execution of Python code, allowing us to conform the language to our specialized needs. In the next section, we'll look at automated unit testing. Testing a set of techniques that could dramatically improve the process of writing a program. Hi, and welcome to our section on unit testing. In the last section, we saw the various approaches to metaprogramming and programmable syntax in Python. In this section, we're going to take a look at the ideas behind unit testing, then move on to several test automation tools we can use to make our testing easier and more useful. In this video, we'll focus on what is unit testing and the ideas that motivate it. Testing is often something of an afterthought for programmers because it tends to be laborious and annoying. Also, we usually have a high degree of confidence in our work, and testing it seems unnecessary. It's also a fact, though, that the confidence is often misplaced. Source code is a complex and subtle language, and it's easy to make mistakes while writing it and not even notice. We all know this from experience, but that doesn't make it any easier to make time for something that is laborious, annoying, and feels unnecessary. So the first question of testing is, how can we do it in a way that doesn't feel like a painful waste of time? Finding a way to overcome that psychological barrier is the first step to creating a testing method that will actually work. For a lot of programmers, unit testing does that by reducing the effort needed to run tests. Integrating testing with the development process and making the tests themselves visibly useful. A unit test is a single small chunk of test code which tests for correct behavior or a single specific flaw within an isolated small chunk of program code. There are reasons for each part of that definition. A unit test is source code because one of the secrets of unit testing is that we put as much as possible of the effort of testing on the computer, where it belongs. The test code tells the computer how to perform the test, which allows us to perform the test often and easily. A unit test is small because a large test is almost inevitably testing for more than one thing. If we want to test for more than one thing, we should write more than one test. A unit test only checks a single aspect of the program code because when a test fails, we want it to tell us exactly what the problem is. A unit test only involves a narrow region of the program code because when a test fails, we want it to tell us exactly what the problem is. Because when a test fails, we want it to tell us exactly where the problem is. If we write a collection of tests that follow these rules, they are a unit test suite. With the proper tools, we can run our whole test suite with a single command, and the output of that command will immediately tell us the status of our code with respect to the test. If a test fails, it tells us what we need to work on next. If it succeeds, it gives us a reason for our confidence in the code it tested. The availability of automated unit testing leads into a programming paradigm called test-driven development. The basic idea of test-driven development is that since a failing test tells us what to do next, we should never write program code except to make a failing test pass. If all the presently available tests pass and the program isn't finished, we first add another test to the test suite, then write program code to make it pass. Doing things this way ensures that there are tests covering most or all of the source code, and that the tests are run often, which makes it very difficult for bugs and regressions to sneak into the code without being noticed. It also lets us break the development process down into a series of short-term goals which produce a visible result when we achieve them. This is psychologically useful because it makes the programming process feel more rewarding. And it's much easier to perform a task that feels rewarding. Further, debugging tends to dominate the time needed for a project, and test-driven development reduces the time needed to deal with bugs. So, applied properly, unit testing principles and tools help us produce better code, do it faster, and enjoy the process more. It's an all-around win. In this video, we've talked at a high level about the reasons for and benefits of automated unit testing and test-driven development. Python includes a framework for automated unit testing, and we'll take a look at that in the next video. In the previous video, we talked about the reasons for and benefits of automated unit testing. In this video, we're going to look at Python's standard unit test package. We'll talk about how to structure a test file, how to write tests, and draw a comparison between what happens and what should happen in these tests. Let's jump straight in. The unit test module contains a framework for performing automated unit testing. Most of that functionality is based around the unittest.testCase class, which we will inherit from to create our own tests. In this example here, we see the basic features of a test case in action: test methods and assert methods. Any methods we define a class inheriting from test case that have names starting with the word test are assumed to be unit tests. In this example, that means that the test addition method is a unit test, but if we had added another method to the class called connect, the unit test module would not treat it as a unit test. A test case class can contain more than one unit test, and should, when those tests are logically related and require the same operating environment to run. Inside our test addition method, which is a unit test, we used a method called assert equal to actually check that the result of the code was as expected. Test case provides a wide range of these assert methods, which test for various relationships between our results and what we expected. We've already seen the assert equal method. It checks whether two values are equal and makes the test fail if they are not. The assert not equal method performs the inverse operation, checking whether two values are equal and making the test fail if they are. The assert almost equal and assert not almost equal methods are for use with floating point numbers. The way computers handle floating point numbers means that numbers, which should be exactly equal, actually differ in their least significant bits. For example, if we square the square root of 7, the result is not exactly 7. So, assert equal will treat it as not equal. However, assert almost equal will recognize that the two numbers are the same for practical purposes. The assert greater equal, assert less, and assert less equal methods check for ordering relationships between their arguments. The assert is and assert is not methods check whether their arguments are references to the exact same object. The assert is none and assert is not none methods are a special case of that, and check whether their single argument is in fact none. The assert is instance and assert not is instant methods check whether the object in their first argument is an instance of the type in their second argument. The assert in and assert not in check whether the object in their first argument is a member of the container in their second argument. The assert count equal method is interesting. If we want to check whether two sequences are the same, we could just use assert equal, but assert count equal is for when we want to check whether two sequences contain the same values but don't care about the order. The method will cause a test to fail if any of the members of either sequence appears in the other sequence a different number of times. So, if A is in the first sequence twice, it has to be in the second sequence twice as well. But we don't care where. Finally, we have assert raises, which functions a little differently because it needs to catch the exception raised by running some code. That's a situation tailor-made for a context manager, and that's what assert raises is. Used in a with statement, assert raises makes the test fail if the code inside the with block does not raise the expected exception. That could seem a little backwards, but it's correct. The test fails if the expected exception is not raised. Sometimes, raising an exception is the correct behavior. For example, passing none into the int constructor should raise a type error, and if it doesn't, that's a bug. I mentioned in passing that all of the unit tests in a test case class should share the same operating environment. What does that mean? That means that each of them expects any external data that they access to be in the same state. For example, each of the tests accesses a particular file, and each of them expects to find the same information inside that file. In this example, we have two tests that both read and write in the same text file. Both of them expect it to contain the same specific information when they start running. In other words, both of them have the same expectations about their operating environment. When we have multiple tests that share the same expectations and they're logically related, we should group them into a single test case class. We give that class a setup method which is responsible. Then, we give that class a setup method which is responsible for making sure those shared expectations are met, and possibly a teardown method which cleans up any changes that setup or the tests left laying around. The name of the class itself doesn't matter. Simply inheriting from test case is sufficient to identify them. The setup method is run before each unit test in the test case. So in our example here, which has two unit tests, setup is run twice. Similarly, tear down runs after each unit test. That way, the changes that one test might make to the operating environment are removed before the next test runs. The starting environment is the same for each unit test in the test case. So that's the basic mechanics of Python's unit test framework. As far as writing test goes, to run the test, we just need to invoke the unit test package from the command line. We tell it the file name of the module we want it to run tests from, and it finds the test case classes in that module. Module creates instances of them, runs all their tests, and gives us a report on which tests passed and which failed. So in this video, we've seen how to write basic unit tests and run them. There are even easier ways to run the test, but we'll look at that after we examine mock objects, which is the topic of the next video. In the previous video, we saw how to use the unit test package to create and run automated tests. In this video, we'll take a look at a sub-package of unit test called mock. The tools in the mock package help us keep our tests isolated, so they aren't made to succeed of fail-based on the behavior of code that isn't supposed to be covered by the test. We've talked about how it's important that unit tests only interact with a small section of code, but how can we arrange for that when so many pieces of code interact with object and functions, originating all over the source tree? One answer is that we replace those objects and functions with mock objects. A mock object is a clever piece of code. It can pretend to be almost any kind of object or function. But instead of doing whatever the original did, it just records what is done with it, so we can check it later. Let's play with a mock object for a moment to begin getting a feel for them. We can access pretty much any attribute of the mock object without defining it ahead of time. The result is another mock object. Similarly, we can call almost any method we want without defining it ahead of time. And the result is yet another mock object. That by itself is enough to let a mock object to replace a large range of functions of the functions and objects that our tested code might interact with. But we can go further if we take the time to pre-configure our mock objects. We can assign non-mock objects to a mock object's attributes, so that accessing the attribute provides a specific value instead of a generic mock object. We can also assign a customized mock object in place of a method, so that we can make mocked method act more like the original, but in a way that's controlled by the test. We do that by passing a return value parameter to the mock constructor, which tells the mock object that every time it's called, it should return that value. If we want the mock to return different values each time it's called, we use a different parameter of the constructor called side effect. We have to know how many times the test will call the mock as a function, so we can provide a return value for each call, but otherwise, this doesn't present a difficulty. We can also make the mock object raise an exception by passing that exception as the side effect or as a member of the side effect sequence. That pretty well covers how to make a mock that can, in a controlled way, stand in for real objects and code while we run our test. However, to really support testing, we also need to be able to check the mock and see if it was used as expected. We've already seen that method calls attribute that mock objects use to track their interactions. But mock objects also have their own assert methods that are usually easier to use than accessing the method calls list directly. The most useful of the mock object assertion methods are assert called with, which checks whether the most recent call to the mock object was done with the specified arguments, and assert any call, which checks whether the mock has ever been called with the specified arguments. So we know what mock objects are for, how to create them, and how to check the record of what has been done with them. That's enough for replacing the parameters of a tested function with mock objects. Mock objects. We can even replace the self-parameter of methods. If we call the method via the class instead of a real instance, what do we do though when the code we're testing reaches out into the system on its own and accesses something we want to replace with a mock object? For example, what if the code we're testing calls time.time? That's where the unittest.mocks patch function comes into play. Patch is a context manager, and it can temporarily replace very nearly any object in any package or module with a mock object. Once the with block exits, the real object is restored to its position. Something to be aware of is that patch doesn't replace every reference to the target object with a mock. It only replaces the single reference that we specify in the first argument. In our example, any code that accesses the time function by looking up the reference in the time module will get our mock object, but if there was any code that had used from time import time to create a local reference to the time function, that reference would still refer to the real time function. If we want to patch the time function for code that has a local reference to it, we need to pass the path to that local reference into patch. Okay, we're pretty much good to go with mock objects now. That means we know everything we need to write powerful tests easily. All we have left to do is find out how to run our test suites, which is the next topic of the next video. In the previous video, we learned how to use unittest.mock to control the environment that our test code runs in so that the tests can remain focused on making sure one thing works properly. In this video, we'll take a look at the unit test package's ability to run many tests at once with a single command. We've seen how to easily run all the tests in a particular file, but for a large project, putting all the tests into a single file would be troublesome. They need to be separated into different files according to logical groupings, or the test suite will become unmanageable. On the other hand, it would be a pain to have to manually tell unit test to run the test in a whole bunch of files. If we had to test, list out each file. Fortunately, there's a way to have our test suite split up into many files and still run it with a simple command. We use a unit testing tool that supports test discovery, which basically just means it looks at the available files and decides for itself which ones seem like test files, then loads the tests from those files and runs them. The unit test package has a basic but useful test discovery tool built in. When we run python-m unit test discover, it searches the current directory for Python s, whose names start with the word test. In addition, it recursively performs the same scan on any subdirectories that contain an init.py file. Once it's collected the names of all the matching modules, it runs the test just as if we'd specified the modules on the command line ourselves. There are a few command line options we can use to adjust the behavior of unit test discovery. The first, which we saw in passing a moment ago, is the -v switch, which makes the test report somewhat more verbose. We used it here so we could see that the discovery had worked properly. We can also use the -p command line option to change the pattern that is used to recognize test files. Here, we've changed it so that file names ending in the word 1.py are recognized as test files. The unit test discover code also recognizes s-s to specify the directory where test search should start. Notice that by making suite act as the starting directory for the search, we've stopped it from being recognized as a package containing the test. If that's a problem, we could supplement the -s option with -t, which tells unit test where to find the top-level directory for this run. By using both -s and -t, we're able to narrow the test search to a particular subdirectory while still running the test in the context of a parent directory. There's a bit of a pitfall to be aware of when using unit test discovery code or any other test discovery that works by importing modules to check whether they contain tests. That pitfall is that the modules are imported. Most of the time, that's not a problem, but if the test discovery code imports a module that was meant to be a program entry point that might result in actually running the program, which is not the desired behavior. It's easy to avoid this problem when we're writing an entry point by wrapping entry point code in if name equals main statement. But if we, or somebody else, left off that check and unit test thinks the file looks like a test file, running unit test discovery code will have surprising results. That's about all there is. Unit test's test discovery tool. It doesn't have many features, but it does have the features that everybody needs. And there's a good chance that it's all we'll need for the majority of projects. For cases where we need more from our test discovery tool, we can use knows, which we'll look at in the next video. Hi, and welcome back. In the previous video, we learned about how to run our test using Python's built-in unit test tools. In this video, we'll look at a free third-party add-on called Knows that gives us access to some additional testing features. Knows is a third-party tool available via pip and the Python package index. It does basically the same job as unit test discover command, but it supports a great deal more control and customization, as well as recognizing a wider range of tests. We're going to look at two specific features among the many the Knows provides. It could generate a code coverage report that tells us how much of our code our tests actually tested. And it can run tests across multiple processes, allowing them to execute in parallel on multiple CPUs. In order to get a coverage report, we first need to make sure that the coverage module is installed. We can do that with a simple pip command. Once we have the coverage module in place, we can enable a coverage report for our tests with nothing more than a couple of Knows command line options. Strictly speaking, only the -- with dash coverage option is required to enable the coverage report. But if we don't include -- cover - erase as well, coverage data from previous test runs will get mixed with our current run, which makes the results harder to interpret. There's a third coverage-related command line option that is sometimes useful. That is the cover package option, which narrows the code coverage report to only a specific package. Focusing the report in this way can make it easier to read and extract useful information. The other Knows feature we're looking at here is the ability to farm out tests to multiple worker processes, and thus spread them across the available CPU cores. To do that, we just have to provide the processes command line option and tell it how many processes to use. If we pass -1 for the number of processes, it uses the detected number of CPU cores, which is probably what we want anyway, so unless we have a specific reason to do otherwise, we should just always use -1. If we look carefully, we could see that it actually took longer to run our test suite on multiple processes. That's because the tests themselves are very low effort. But launching a worker process is not. Fortunately, that's a fixed cost. So when we start running larger test suites containing more expensive tests, we start seeing the benefits of parallel execution. This was just a taste of the sort of features that Knows supports. And that's without writing our own Knows plugins to customize it further. It's a very capable system, so if we find ourselves needing a particular feature from our test runner, A good first step is to see if nose already has that feature. In this video, we learn how to take advantage of a couple of features of the nose test runner. In the earlier videos of this section, we learned to use the unit test and unit test.mock packages to help us write automated tests, and learned about the process of test-driven development. In the next section, we're going to take a look at the reactive programming paradigm and RxPy. Hi, and welcome to our section on reactive programming. In these videos, we're going to get a handle on the concepts of reactive programming and then take a look at the RxPy reactive programming framework. In this video, we'll work on solidifying our conceptual understanding of reactive programming. There are a lot of different and valid ways that I could define reactive programming. It's a matter of perspective and focus which of them is the best definition. We're going to cover several in this video. Perhaps the most fundamental definition of reactive programming, at least in terms of what we need to think about to implement a reactive programming system, is that it's a publish-subscribe model of event handling. In the traditional nomenclature of reactive programming, there are observables and observers, which encapsulate the behavior of event publishers and event subscribers, respectively. In a reactive programming system, everything, or at least as much as possible, is an observable or an observer. So far so good, but publish-subscribe isn't really exciting. Reactive programming comes into its own when we recognize that an observable is conceptually very similar to a list, which means functional programming tools such as map and reduce have powerful analogies, analogs, that apply to observables. And so, our second definition of reactive programming is that it's event-driven functional programming. The idea that we could, for example, take two observables, map a function over one of them, merge the result with the other, and reduce that merge sequence to a new value is a powerful one. We can describe all of the operations we want to perform ahead of time, and whenever a new value comes out of one of the root observables, it will cascade through our whole processing chain without further effort on our part. Functional programming operations are mostly stateless, and when they're not, the state is at least easy to define and keep contained. That means that our event-driven, mostly stateless reactive programming systems are very well suited to asynchronous or parallel execution. Thus, our third definition of reactive programming is that it's a systematic way of writing high-performance asynchronous or parallel code. So what is reactive programming? It's an event-driven paradigm in which event sources can have functional operators applied to them to create new event sources, which is desirable because it results in programs that work well in asynchronous or parallel execution environments. In the next video, we'll put together a very bare-bones reactive programming system from scratch. In the previous video, we talked about what reactive programming means in a theoretical way. Now we're going to get very concrete and build a simple reactive programming system, then build a demo so we can watch it in action. The roots of formalized reactive programming are in statically typed languages, particularly C#. That's of little concern to us as users of a language based around inherent typing, but it does mean that the standard presentation of these ideas is heavily intertwined with types, templates, interfaces, and anonymous functions. To make it easier to transition from this presentation to the other documentation and discussions available on the web, we'll be a little less Pythonic here, and perhaps a little more C#ish. That said, on to the coding. Arguably, the single most fundamental element of a reactive programming system is the observer interface, the definition of how we can notify an object that the next item in a sequence it's watching is available. What we've got here is an abstract-based class, the closest Python equivalent to a C# interface. Our observer class doesn't define any functionality at all, just method names and signatures, and guarantees that classes, which inherit from it, will have to implement at least the onEvent method. For complete functionality, they'd have to implement onException and onComplete as well, but that's not required. So the intent is that an observer will have its onEvent method called. once for each element of the sequence, followed by its onComplete method if the sequence terminates while the observer is watching it. If something goes sideways, the onException method would be called instead. For an observer to be useful, there must also be an observable. So here we see the beginning of that class. Like observer, observable is an abstract-based class. Although in this case, we provide meaningful default implementations of all of its functionality. The subscribe method, which we're looking at right now, is how an observer connects to the observable, registering itself as a consumer of the events that the observable emits. Alright, so how do we actually emit events? These three methods, one for sending normal events, one for sending exceptions, and one for sending the "this sequence has ended" event, take care of that. In each case, they do a bit of error checking, then loop through the registered observers and invoke the appropriate method. These methods have names prefixed with a single underscore, marking them as not part of the observable class's public interface. They're helpers to make subclasses easier to write. That can't possibly be a complete reactive programming system, can it? Yes and no. It is fundamentally complete, but it's lacking a great many refinements. And in no way is it ready for a production environment. It will serve nicely as the spine for our demo program, though. So let's move on to that. For our demo, we're going to make a program that prints messages, loosely representing the sounds we might hear in a zoo. The animals will be represented as observables, emitting events, representing sounds at random intervals. We'll use merging and mapping to combine and modify the event sequences before finally printing out the resulting sequence. So first of all, we have our animal class, which is an observable, and the animal event helper class. The animal class contains some basic information and a coroutine which will run asynchronously and occasionally send events to the animal's observers. Looking at the code here, we can see that an animal is effectively a sequence of noise events, then a die event immediately followed by the completion of the sequence. We want some of our animals to be capable of creating loud noises. Instead of adding that capability to the animal class, we'll create a mapping over the sequence of events, which replaces randomly selected noise events with loud noise events. This mapping is both an observer, so that it can subscribe to the sequence of events, and an observable. Because the sequence of modified events is still a sequence of events, and not much use if another observable can't subscribe to it. This is fundamentally what happens in any reactive programming system when we apply an operator to an observable sequence to create a new observable sequence. However, in almost every case, a real reactive system provides us with a quicker, easier, and usually more efficient way of doing it. It's rare indeed to actually create a class that's both observer and observable for ourselves. There's one more place we need before we start putting things together, and that's a way to display a stream of animal events. Another observer is the obvious choice for that, and it turns out to be quite easy. All we need is a constructor and an appropriate onEvent method. Now that we've got all the pieces, how do we put them together to achieve our goal? Well, first, we make our animal objects, and then use the sometimes loud and output classes to create our modified composite sequence and display it. Then, we need to schedule the run methods of each animal for asynchronous execution via async.io, which happens implicitly here when we pass them as parameters to gather. Our main.py file actually runs the async.io event loop. So now, we just sit back and watch the pseudo cacophony of our imaginary zoo. Did you notice how the meat of our program is boiled down to a single line of code? Sure, we have a whole file devoted to framework, but that's reusable. We also have the sometimes loud and output classes, but the only reason they're here is so we can see exactly what happens at each step of this program. In a real system, output and sometimes loud would have used built-in functionality that mapped a function on the sequence, as we'll see in the next video, all of which leaves us with a single line of code that composites several observable sequences and transformations and defines most of the behavior of the program. That one line demonstrates the power of reactive programming. In this video, we implemented and used a basic reactive programming framework. In the next video, we'll take a look at a fully fledged reactive programming framework called RxPy. Hi, and welcome back. In the previous video, we built a bare-bones reactive programming system and used it to implement a demo program. In this video, we'll be looking at one of the more widely used reactive programming frameworks called reactive extensions, which is often shortened to ReactiveX or simply Rx. Rx is not part of a standard Python installation, so we'll need to use pip to install it. No problem, it's only a single command. If you prefer to install to your Python system library instead of user library, or you're working in a virtual environment created by the -- user from that command. Once we have Rx installed, we can move on to the fun stuff. Like our example in the previous video, Rx provides observer and observable classes, and they encompass the same basic functionality. The largest visible difference is that Rx's observable class has a large number of factory methods that can be used to construct special-purpose observables, especially observables that produce a sequence based on one or more other observable sequences. In other words, most of the operators and operations that we'll use to construct our reactive data flow are methods of the observable class. Let's take a moment to rewrite our demo from the previous video in Rx, and we'll see what that means in practice. The animal event class can stay the same, since it's just a data structure and doesn't know anything about who's using it for what. Our animal class changes quite a bit. The run coroutine method goes away, and in its place, we have a somewhat simpler generate event method. That name isn't significant, by the way. It's just a reasonable name I picked because it describes what the method does. The generate event method by itself doesn't encompass the entire functionality of the old run coroutine method, though. It knows how to emit an event, but it doesn't know how to wait a short while and do it again. That's where the asObservable method comes into play. That method uses one of the observable class's factory methods to create an observable sequence that's backed up by what is functionally a generator, although it's not implemented as one because that concept doesn't exist in every language that Rx is portable to. So instead of a real generator, we provide it with a state variable, which in this case is just the animal instance, along with functions it could call to check whether the sequence continue, update the state, get the next value of the sequence, and determine how long to wait before producing the next value. The factory method also accepts a scheduler object, which we'll come back to shortly. So what we're asking for here is an observable that produces animal events at random intervals from 0 to 10 seconds. Now the animal class may be a little simpler than it used to be, not a big difference. However, take a look at what happens with the sometimes loud and output classes. They're not classes anymore at all, just functions, and significantly simpler. The sometimes loud function takes an event and returns an event, and will use it to map from one observable sequence of events into a new one, just as you'd expect in a functional programming environment. The output function takes an event and returns none, which is again what we'd expect for a side effect in a functional system. So what do we need to do to put it all together? Well, first, we create an async IO scheduler, which is an Rx scheduler that specifically integrates with an async IO event loop. Rx contains quite a few different scheduler implementations that integrate with various event loops available in Python, as well as one that uses Python threads to implement scheduling. Regardless of which scheduler we use, the scheduler's job will be to decide when time-based elements of our event pipeline occur. That means, in this example, that the scheduler is going to be deciding when our animal observables produce new values. After creating the scheduler, we create the animal objects and their observable sequence of events. Now comes the interesting part, where we tell the computer how to combine and process those observable sequences. First, we merge the elephant and lion sequences into a single combined sequence and process that sequence through our sometimes loud function to create a new sequence we call louder. The select method used here is the direct equivalent of the map function in a functional programming environment. Next, we merge the louder sequence with the remaining animal sequences and tell the system that whenever a new value arrives at the front of that merged sequence, it should call the output function on that value. The do action method used here is not equivalent to map because it doesn't transform the sequence, just performs an action on each element of it. The do action method is for side effects. Finally, we subscribe to the completed event on the out observable sequence, which is the same as the sequence merging all event streams into one. Since the do action operation returns its input sequence unchanged. When the sequence is complete, we set a result value on the done future. Since we used that future as the parameter to run until complete in our main.py file, setting its result value terminates the async IO event loop and our program ends. Our demo here has shown us the merge, select, and generate with relative time factory methods of observable. But that's just the tip of the iceberg. There are so many observable factories that it would take more time than we have just to give a short description of each one. Each of them gives us a useful way of constructing an observable, usually, but not always, based on one or more other observables. Python's interactive shell and help function are our friends here. There's a lot to be learned by poking around in the observable class. In the meantime, we're going to talk about a few of the very best observable factory methods that we haven't seen yet. First on that list is observable.create. This is the recommended way of creating a completely customized observable. The create method callable as its parameter and calls that callable each time an observer subscribes to the observable. Here, we've created an observable that says hi when an observer subscribes, and then never produces another value. Not the most useful of sequences, but it serves to illustrate the idea. We could take the basic framework and construct an observable with any behavior we like from it, without subclassing the observable class and without re-implementing, probably incorrectly, the internal machinery that keeps observables synchronized and functioning properly in an asynchronous or parallel environment. Next up is observable.selectMany, which is a more generalized version of select, where select applies a function to each member of the sequence to create a new sequence from the function return values. SelectMany expects a function that returns an observable sequence and concatenates those sequences. That means that the function applied by SelectMany can remove elements from the sequence by returning an empty sequence. And it can insert values by returning a sequence containing more than one element. As with select, the values added to the result aren't necessarily the same values that were passed to the function either. So, SelectMany can produce a sequence containing more or fewer values than the input sequence, and the values can be determined however we choose. Empty sequences and sequences of one value are easy to create using the empty and return value factory methods, respectively. Similarly, it's easy to construct an observable sequence of any already known series of objects using the of or from iterable factory methods. While we could use SelectMany to remove unwanted events from an observable sequence, it's easier to use the where method, which applies a callable to each element of the input observable sequence and returns an observable sequence containing only those elements for which the callable returned true. Now we've seen that fundamental ways to add and remove events observable sequences, so what about processing them? We could just use select and select many to do all of our processing. But Rx provides us with min, max, average, count, distinct, group by, slice, sample, sum, and zip methods, just to name a few of the available tools. In this video, we looked at the reactive extensions for Python, used them to re-implement our zoo demo, and looked at some of the broader possibilities of the framework. In the earlier videos of this section, we discussed what reactive programming is and implemented a bare-bones reactive framework to help us get a handle on the concepts. In the next section, we'll look at microservices, which are very small server processes that are meant to work together to create the desired result. Hi, and welcome to our section on microservices. In the previous section, we looked at reactive programming and the ReactiveX framework. In this section, we're going to take a look at what a microservice is, why we might want to structure our programs as microservices, and how to use some common Python tools to create them. In this video, we're going to be looking at microservices from a conceptual perspective. When we need a new feature for a project, there's a temptation to just add it to the project's main program and continue on from there. Sometimes that's entirely appropriate, but in many cases, it's actually better to make the feature a distinct program in its own right. There are several reasons why a feature might be better off with less tightly integrated into the system. The most important ones are flexibility, scalability, and durability. It's easy to understand the flexibility benefit. Modular programs inherently consist of a bunch of modules that we can reuse in the future. So, every time we write our code as an independent module with a well-defined interface, we're making an investment that will make it easier to adapt to the changes that come in the future. The scalability advantage comes into play when our modules are actually separate processes, allowing separate instances to be run on multiple processors, with the load balanced across them. The durability advantage also comes into play when the modules are processes, because processes are mostly safe from the bugs that crop up in other processes. And because processes are mostly safe from the bugs that crop up in other processes, and because a failed process can often be restarted without needing to take down the whole system. Those advantages all apply to many circumstances. They're the same advantages that drove the development of microkernel operating systems back in the 1980s. But the term microservice specifically refers to applying them to web applications. This means that instead of writing one server program that handles all of the logic of our web application, we'll write one or more servers that handle most of the front end and call on a bunch of different special purpose servers to handle all the back end work and any remaining parts of the front end. Each special purpose server should do a single well-defined job as well as possible and not care about anything else. Those special purpose servers are microservices. And usually, using a microservice design gives us better uptime. Uptime lets us scale up to take advantage of a server farm or cloud hosting system and helps us adapt to the ever-changing web more quickly. So to recap, when our server is actually a collection of servers, each of which has a narrow and well-defined job to do and does only that, we're using a microservice architecture. As an added benefit, the interfaces between our microservices constitute an application programming interface. So if we get to a place where we want to expose an API for the world to use, all we have to do is adjust our authentication and authorization code, and possibly our routers, to allow external entities to access some of those interfaces. In this video, we've looked at some of the advantages of process-based modularity and seen how applying those principles to web applications results in a microservice architecture. In the next video, we'll learn how to use the Flask package to quickly and easily construct a microservice that uses HTTP and representational state transfer, better known as REST, to provide its interface. In the previous video, we took a look at what a microservice is and why structuring our servers as collections of microservices is helpful. In this video, we'll take a look at the practicalities and use Flask to construct a functioning microservice. Microservices can pretty easily be divided up into those that use web technologies such as HTTP to communicate with each other, and those that use a dedicated inter-process communication or remote procedure called mechanism to communicate. There are advantages to each depending on the specific needs of a project, and neither is inherently easier to work with. But I'm going to refer to microservices that use web technologies to communicate as high level, because they're inherently closer to the level at which users operate. Conversely, microservices that use specialized protocols I'll refer to as low level. In this video, we're looking at high-level microservices which usually use HTTP to communicate and provide representational state transfer-based programming interfaces. Using stateless protocols for communication makes these microservices easy to load balance and easy to swap in and out for maintenance. For this type of microservice, we could use any of Python's several production-quality web application frameworks or toolkits. But we're going to use Flask. Flask is laser-focused on making it easy to write handlers for HTTP requests and doesn't really do anything else. That makes it very well suited to writing a microservice that processes a few specific requests while using minimal resources. Flask isn't part of a Python standard library, but it's easily installed using pip. As always, you can add --user to the command to install into your personal Python package library, and you can install it into a virtual environment if you prefer. Flask is designed to interface with a front-end web server or proxy using the Web Server Gateway Interface, or WSGI, which is standard for Python web applications. However, we'll just be using its built-in development server for our simple little demonstration. So what shall we build? Let's build a microservice that maintains a database of information about people: first name, last name, age, and for interest's sake, whether or not they're members of a particular club. We'll use HTTP's post, get, put, and delete methods to allow the microservices clients to create, access, update, and remove records from the database. And we'll provide the data in JSON format, but accept input using the normal HTTP form encoding. Those choices are all very normal. Only slightly less common would be to have incoming data be in JSON format as well, which we accommodate by calling Flask's request_get_JSON function when we needed the data. Okay, so what boilerplate code do we need to get a Flask microservice on its feet? Not much, as it turns out. These 2 lines are sufficient to get the Flask system in place. It doesn't actually do anything except return 404, not found errors in response to any request, but it'll respond. So how do we make Flask handle a request? There are actually 2 ways to do it. One which is incredibly simple, and one which is more flexible and better encapsulated. The simpler way is to use the app.route decorator to tell Flask that a particular function will handle request for a given path. That's all that's needed, apart from making the function actually do something useful. However, for our microservice, we want to use HTTP methods on the same path to produce different results. We could use app.route and a bunch of if-else-if blocks in the function to handle that. But there's a better way. Flask supports pluggable view classes and specifically has a method view class that has a different handler function for each HTTP method. The appropriate function processes each request based on which HTTP method was used. There's a slight complication to this because we don't actually always want to use the same path. Sometimes we want an object ID in the path, and sometimes we don't. There's only a small complication though, because we could register the same pluggable view on several different combinations of path and method, which is exactly what the endpoint.register function here in endpoint.py does. Each registration of the view consists of one call to app.add URL rule. The first one registers the get method with no object ID and fills in value to use for the ID parameter when calling the get function. The second one registers the post method with no ID and no default because our post function doesn't accept an ID parameter at all. The third registers the get, put, and delete methods when there is an ID. Between those registrations, that covers all the use cases common to a single programming interface endpoint in representational state transfer. Now that we've got our method dispatching ready, how about we put together our actual handlers for manipulating person objects? Here we see our person API class, which has one function for each of the operations we want to enable on our person database. For the post and put functions, we get data from the request using the request.form object, which is a dictionary-like object containing the decoded data from the request body. As a side note, this looks like it's not thread safe, but it actually is. Everything in Flask is multi-thread and multi-process safe. It's just wrapped in a simplifying semantic layer that simulates a single-threaded single-process system. The post function doesn't have any code to handle missing data except for the member value. That's because if we try to access a missing value from request.form, an exception is raised that causes Flask to return a 400 bad request error, which is exactly the right thing to do in that case. The put function, on the other hand, handles those exceptions itself so that it can decide which values to update and which to leave alone. The get function might be called with an integer ID or with none for the ID, and needs to handle both cases. That's easily done with an if statement. In the case where the ID is a number, it's supposed to return the state of the object with that ID. If ID is none, it's supposed to return a list of all of the objects. All the methods return JSON formatted data, which is done by using Python's standard JSON package, and specifically the JSON.dumps function, which transforms Python data structures into JSON formatted strings. We also need to provide the content type header with a value of application JSON as a matter of good practice. Between those two things, in the return statement, we're also providing the HTTP status. That could be omitted, but since we're returning error codes in some places, it makes sense to include the status code, even when it's not an error. To do a test run of our microservice, we're going to need to start up Flask and tell it to serve our microservice. The demo Flask package also contains a module called test.py that we can use as a client that connects to our microservice and put it through its paces. It will add, delete, list, and modify a couple of database entries, and also try out a bad post request to show that the error handling is working. There's one more part of the Flask demo microservice that we haven't talked about, and won't in detail. That is the person.py file, which contains a simple interface with a SQLite 3 database for actually storing and retrieving objects. Feel free to look at it, of course, but it's not particularly relevant to the topics of this section. And a production system should probably use SQL Alchemy, Redis, CoachDB, etc. In this video, we looked at the details needed to use Flask to create a RESTful microservice and put that knowledge to use by building a simple person management microservice. In the next video, we're going to look at using the nameco package to create microservices that communicate using remote procedure calls instead of HTTP methods. Hi, in the previous video, we looked at how to use Flask to whip up a microservice that used HTTP to communicate with its users. In this video, we'll take a look at nameco, which will help us put together a microservice that communicates using the advanced message queuing protocol, which we can safely think of as a remote procedure call protocol, though that's actually only a part of what it does. Using HTTP to define the interface for our microservice has the advantages of familiarity and good integration with web technologies. But there's a certain amount of overhead involved in mapping the request and input data onto the functions and parameters that are actually meaningful to us. We could come up with abstractions that hide that part of the process, of course. That's essentially what the authors of nameco did. Although they used AMQP instead of HTTP to transport data and events. Installing nameco itself is easy, using pretty much the same pip command we always use. Be aware though that nameco won't actually work until we install some other software as well. More on that later. Looking at the nameco version of our person service, it's clear that the effort paid off. Our service is defined by a class with a name attribute and several member functions decorated with RPC. The member functions interface with the same database interface class we used in the previous video. In a very straightforward way, it would even be reasonable to combine the two into one class, and that's it. The complete definition of our microservice using nameco. Pretty sweet, right? It really is, but every cloud has a silver lining. And there are things we need to be aware of before we choose nameco or any similar tool. The first thing to be aware of is that nameco doesn't provide the complete AMQP infrastructure, it just connects to it. The AMQP infrastructure is responsible for conveying messages between connected programs in a way that is quick and reliable. That means we need an AMQP server running somewhere that nameco can find it. That means an AMQP server accessible to the microservice and an AMQP server accessible to the microservice's users. And those servers need to be connected to each other. They could be the same server, of course, but they don't have to be. Nameco recommends the RabbitMQ AMQP server, which can be downloaded from its own website. The installation is relatively uncomplicated, and there are detailed instructions on the site. Now that we have an AMQP server installed and running, can we connect to our service and manipulate person objects? Technically yes, but we need to use nameco to write the client too. AMQP isn't as simple to work with as HTTP, and the RPC mechanism adds an additional layer of complexity. We don't want to work with that raw. The first way we can interact with our microservice is manually using the nameco shell, which is an enhanced Python shell. First, we have to run the microservice, which we'll do in its own command window. Then we start the nameco shell and use the end.rpc object to access the functions of our microservice. It looks like we're just calling the functions, but actually we're communicating with the microservice through the AMQP protocol. The second way we can interact with our microservice is to create another microservice that depends on it. This test service periodically exercises the person service. It also demonstrates how to link one service to another, so that one of them is able to access the other. The key is the line that creates an RPC proxy instance on the class. When the service runs, it's able to access the functions of the specified remote service through that object. To run our test, we need to start both the person microservice and the test microservice, which we can do with a single command. You may have noticed that we return the object ID from the create function rather than the created person object itself. That's because we can't return the person object. Nameco functions can return any data that can be represented as JSON, but that doesn't include instances of arbitrary classes. The same goes for parameters that are passed into a microservices functions. They need to be within the limits of JSON. This isn't actually a more stringent restriction than we saw in the Flask microservice. It's just that with Flask, it was obvious we were sending data across the network in JSON format. So that limitation was obvious. With Nameco, the requirement is the same, but the reason for it is easier to miss. In this video, we looked at using Nameco's remote procedure call mechanism to implement a microservice, which simplifies the code significantly, at the cost of requiring that we set up an AMQP infrastructure, and more difficult interfacing with systems outside the AMQP network. In the earlier videos of this section, we looked at microservices are philosophically and what their advantages are, and implemented an HTTP-oriented microservice using Flask. In the next section, we'll look at how to interface between Python and compiled code to optimize performance bottlenecks in our code and access libraries written in other programming languages. Hi, and welcome to our section on integrating compiled code into our Python programs. We're going to take a look at the benefits and drawbacks of our compiled code and see two ways of making the connection between Python's managed environment and code that runs directly on the hardware. In this first video, we're going to see what we can gain by using compiled code for part of our program and what it can cost us. Python is a very productive language, but it's not all things to all people. Sometimes we need to interface with code written in a different language. One reason for doing this would be if we need to access some functionality that was written in a different language. As long as the code in question is in a dynamic library that has a C-compatible interface, it's relatively easy to call the code from within Python using the foreign function interface provided by Python's standard ctypes package, which we'll discuss in the next video. Alternatively, maybe we need to write some code that runs close to the metal, either to maximize the performance of an algorithm that's proven to be a bottleneck in our project, or to interface directly with some piece of hardware, in which case we'll want to be compiling custom code and linking into the Python environment. That's most easily done using a tool called Cython, which we'll discuss in the third video of the section. Those three reasons, interfacing with existing code, optimizing a bottleneck, or driving hardware, cover more or less every case while working with compiled code is actually a good idea, because there's some significant downsides to working with compiled code. First and foremost, among these downsides is the fact that it's easy to create ridiculously weird bugs when we work at that level. Both ctypes and Cython allow us to make a horrible mess in the program's memory, potentially producing any conceivable bug or error. When we're lucky, that results in the flat-out termination of our program due to violating the constraints of the operating system's protected memory manager. I say that's lucky because if that doesn't happen, it means we've made an effectively random change to some part of our program state. And who knows what they'll do. The second downside is that it makes distributing our program more difficult. For a normal Python program, we can distribute a single .pyz file to our users or upload a setup tools compatible source package or operating system neutral wheel file to the Python package index. Using compiled code means we have to worry about which operating system and hardware architecture our users employ, and provide separate packages for each combination we want to support. The third downside only applies if we're writing our own compiled code, primarily for the use cases where Cython is most useful. The problem is that it can be non-trivial to actually get a compiler installed and working, particularly for people who aren't used to working with compilers. Not only that, if we distribute our project as source code, our users need to go through the same hassle. Between the danger of bizarre errors and the annoyance involved in creating and distributing projects that use compiled code, we should generally wait until we have a compelling reason before we take the step of creating or interfacing with compiled code. Now we have a pretty good grasp of the benefits of interfacing with compiled code. It gives us access to C-compatible libraries written in other languages. It lets us optimize the performance of critical algorithms, and it lets us interface directly with hardware or low-level drivers. Similarly, we know what the drawbacks are, the potential, seemingly inexplicable errors, and a generally higher level of annoyance and difficulty throughout the development and distribution process. In the next video, we're going to look closely at the ctypes package and use it to interact directly with the C standard library. Hi. In the previous video, we discussed the benefits and drawbacks of using compiled code. In this video, we're going to narrow our focus to the Python standard library's ctypes package, which allows us to interact with dynamic libraries from within Python. Probably the most common need to interact with compiled code is when there's a library out there that does exactly what we need. But it's not a Python library. Instead, it was written for C, or at least has a C interface. We're not going to let a little thing like that stop us. Instead, we'll use ctypes to create an interface module for the library. For basic usage, ctypes is very simple. We import it, load the dynamic library by file name, and call a function in that library. The cdll constructor we're calling here creates a Python object representing a dynamic library containing C functions. There's a little complexity in picking the library file name. Because different operating systems have different naming conventions for libraries, libc.so.6 is the file name of the C standard library on current versions of Linux. Ctypes includes a utility function to help address this difficulty, called ctypes.util.findLibrary. If we pass a base name into findLibrary, it will try to find the full name of the version installed on the system. That's pretty useful on Linux and Mac OS X, but less so on Windows, because Windows dynamic libraries handle multiple versions in a very different way. It's also worth noting that while passing the string C into findLibrary, we'll find the C standard library on Linux and Mac OS X. On Windows, the same library is rather arbitrarily called MSVCRT. For cross-platform library loading, we need to be able to specify several alternate names for the library. Try findLibrary on those names, and fall back to trying the raw name if findLibrary fails. There's a load library function in the demo underbar ctypes/lib c.py file included with this course video that demonstrates this. Once we have the library loaded, we have access to the functions exported from that library, which are exposed as attributes of the library object in Python. We saw that earlier when we called C's printf function. Now it's important to know that there's nothing in a C-shaped shared library that tells users of the library what the parameter types of a function are, or the return type, or even how many parameters the function has. That information is used when compiling the library, but it's not part of the end result. That means it's up to us to know how the function is supposed to be used. For example, the C library contains a quick sort function called qsort, which is intended to accept several parameters. As you can see here, if we omit those parameters, ctypes has no way to know we're making a mistake and bad things happen with no warning. If we're planning on making systematic use of a foreign function, or especially if we're going to expose it as part of the interface of a module we're writing, we're well advised to tell ctypes about the function's signature, which we can do by assigning to the function's argtypes and resttype attributes. The argtypes attribute should be a list of C data types defined in the ctypes package, while resttype should be a single one of them. As you can see, providing this information to ctypes significantly improves the error handling for a foreign function. The @of function returns a double precision floating point number, but ctypes wouldn't have any way know that if we hadn't told it. When it doesn't know better, it just assumes the return value is an integer, which works in many cases, but would have been useless here. It's pretty common for C functions to accept a pointer as one of their parameters, and fill in a value at the address the pointer refers to. Naturally, ctypes allows us to work with that sort of interface by letting us create objects that represent memory locations and pass them by pointer to the functions we call. The cscanf function works like this. Here, we're creating two C-style variables called integer and decimal, and then using the scanf function to fill them with values based on user input. The byref function tells ctypes that we're not passing the value of the variable to the function. We're passing its memory address, so the function can store something there. Another common behavior of the C functions is for them to fill bytes into a character buffer. We can use the ctypes create string buffer function to allocate such a buffer, and then use the result as a parameter for functions that want one. There's no need to use the byref function because a character buffer is inherently by reference. There's just no other way to do it in C. There's a pitfall here, one that's been tripping up C programmers for decades. Our string buffer has a specific length, but the function we're passing it doesn't know what that length is. If it starts writing into the buffer and goes on beyond the end of it, the program will either crash or begin behaving strangely. Always make sure your buffer is at least large enough for whatever will be written into it. Another thing that is not available from looking at a C shared library is the layout of any data structures that the functions use. Again, ctypes gives us a way of filling in the missing information. The CTM structure, which is used for representing date and time information, looks like this. The translation into ctypes is straightforward. We need to create a class inheriting from ctypes.structure, and in that class, we need to create a list called fields, containing tuples of field name and field type. Once we've got that, we could create instances of the class and assign the attributes as we'd expect in Python. But we can also pass it into C functions as a parameter, either directly or by reference. And we can use it as part of the signature of a foreign function. The ctypes package provides support for pretty much every feature of the C language, but we've now seen the ones that are most useful for calling into a library function and using its results. In this video, we've seen how to use the ctypes package to tie into the interface of a C dynamic library, calling the functions and receiving their output from within our Python code. In the next video, we'll see an easy, as such things go, way to write compiled code modules so that they can be imported and called directly from Python. Hi, in the previous video, we took a look at using Python's standard ctypes package to access functions stored in compiled C-compatible dynamic libraries, which is a quick way to gain access to functionality that was written in other languages. In this video, we're going to look at a third-party tool called Cython, which is another tool for bridging the gap between Python and software that has been compiled to machine code. If we had a situation that called for us to implement part of our project in compiled code, it would be entirely possible to do it by creating a dynamic library containing the code and call into it with ctypes. But that's a roundabout way to get where we're going. We'd end up writing a lot of the code twice, once for the sake of our compiler, and then again to tell ctypes about details, like function signatures and data structures. That's inefficient and violates the don't repeat yourself principle of programming. There's a tool that's better suited to this situation. And as you've surely guessed, that tool is Cython. What Cython does is translate a Python source code file into a C source code file containing the equivalent calls to the Python C API and wrap it in the boilerplate necessary to turn it into a Python binary module. That would be useful enough by itself, but Cython also allows us to interject calls to C functions and low-level data access operations into the module. The end result is that we could pretty much just write our compiled code as if it were Python and still gain the speed or low-level access that prompted our need to compile. The amount of work this saves us over using the Python CPI API directly is considerable. The 100-line example included with this video translates into more than 5,000 lines of C when it's compiled. Let's go through that example piece by piece and talk about the differences from plain Python. The first thing to note is that in addition to normal imports of Python packages, Cython also allows two additional import mechanisms. The first is called cimport, and what it does is import the signatures of compiled functions and data structures from pre-prepared libraries. In this case, since Cython comes with a pre-prepared library of all of the Python C API functions, we're able to use that mechanism to import the needed information about Python's low-level memory allocation and deallocation functions. The second additional importing mechanism is cdef extern from. When we don't already have the signature of a compiled function available, we use the syntax to make it available in the Cython code. The indented block can contain any number of function declarations, type defs, structure definitions, and so on. But they don't have to be precisely correct, just close enough that Cython is able to generate proper C code. A cdef extern from block references a C header file, which is automatically included in the generated C code. While we could simply use the normal Python syntax for the class statement, prepending it with a cdef gives the ability to store raw data values in predefined variable members of the class instances. The num values variable, for example, is just a chunk of memory storing the bits that represent an integer value. It doesn't have any of the extra data needed to turn it into a Python object. This is a bad thing in a way because it means that Python can't do any of the smart things it does to help us write good code quickly. But we wouldn't be working with these tools if we didn't have a reason to do some of that work for ourselves. So here, we're defining an extension type called statistical array, which contains a pointer to a memory location and two integers. The memory location is supposed to contain double precision floating point numbers. These are raw machine-level values, and while primitive in comparison to Python values, they're very fast because they can be fed directly into CPU operations. Here, we have the functions that set up and dispose of instances of the statistical array class. Notice that the setup function is called cinit, not init. Actually, a Cython cdef class can have both. The cinit function's job is to set up the raw variables for the class instance, and the normal init function is supposed to set up any normal Python variables it contains. the cinit function is called first, and it's not guaranteed that self will actually be a valid Python object itself yet. So it should confine itself only to initializing the raw variables. The reason cinit accepts the extra positional and keyword arguments is so that if a Python class inherits from our class and adds more parameters to the signature of init, the cinit function will still work. At the other end of the process, we have the dealloc function, which needs to release any specially allocated resources associated with the class instance. In this case, we allocated a chunk of memory in cinit, so we need to release that memory here. Now here, we're defining a few of Python's normal magic methods, allowing us to iterate over the values stored in our object and access them by indexing. The thing to notice here is how little has changed from what we'd be doing in a pure Python implementation. The only real differences are the type definitions we provided for every parameter and local variable. We didn't actually have to do even that, but it lets Cython generate planned C code for a lot of the operations we're performing, which means we're using the CPU directly instead of the Python virtual machine. We're trading flexibility for speed. The previous functions were all defined with the def keyword, as normal for Python, and the functions created operate as if they had been defined in a normal Python module. Cython gives us two other options, though. Instead of def, we can use cdef, in which case the function is much faster to call, but is only for use by other Cython code. This is great for internal help functions and such, or we can use cpdef, in which case the function is accessible from normal Python, but is almost as fast as a cdef function when called from Cython code. We've chosen cpdef here because we want to expose the full feature set to any Python code that uses our compiled module, but we also expect to use the same functionality from within our Cython code. Here, we're getting to the reason we called our class a statistical array. We're implementing several discrete statistical calculations using the values stored in the class instance. You don't have to care what mean, variance, and covariance actually do, but let's take a look at how they do it. In the mean function here, we see a loop that calculates the sum of the values stored in the array. If we were running that code in Python, each cycle through the loop would involve several dictionary lookups and function calls. In the code that Cython generates, it's 4 lines of C code that translates into only a few machine code operations. That's possible because we told Cython that the index variable should be a C integer. And because Cython is smart about handling loops with C integer variables, we gain a similar benefit in the variance and covariance functions. Again, we just use Python syntax and give Cython additional information that it can use to optimize the generated code. There is one unusual thing to note with covariance, though. At the end of the first line, we see except -200.0. What is that? Well, as with most of these functions, we gave the covariance function an explicit C return type of double. That's a big gain in terms of speed, when the code call in the function is also Cython and stores the return value in a cdef double variable. But there's a downside. Normally, Cython would use the return value to signal that an exception has been raised. But how's it supposed to do that when we change the return type and it doesn't know which values are even valid now? Well, we'll tell it. Adding except -200 means that if the return value is -200, Cython should check to see whether an exception has been raised. If we'd left off the question mark, it would mean that -200 always means there's an exception, which is a bit faster, but we can't go that far because -200 is still a potentially valid return variable. Notice that we don't actually return -200, we just raise an exception as normal. Cython takes care of the rest. Here, we have a couple of functions that are built up using the earlier functions as building blocks. Thanks to our use of cpdef, when we define the variance and covariance functions, there's very little overhead involved in calling those functions from here. Okay, well and good. We've written a somewhat useful Cython class. Now, how do we make it available to Python code? Well, we have to compile it. First of all, that means we need to have a compiler. The documentation on cython.org has a tutorial entry and appendix going through that process. And I suggest referring to them if there's not already a compiler on your system. If we have a compiler, installing Cython is just a matter of asking pip to grab it for us. The install can be a little slow because it needs to do some compiling. During the installation, just be patient while it finishes. Once Cython is installed, we need to create a setup.py describing how to build our extension. For the base case, that's very straightforward. The source code we were working on is saved in statistics and .pyx. Pyx is the standard file name extension for Cython source code files. Once we do that, the last step is a snap. Once the build.ext command is finished, we should have a compiled extension sitting next to our .pyx file. Now all we have to do is import it and use it. Notice that when we cause an exception in the compiled code, the traceback is fully filled in and points us to the cause and location of the problem. That's a Cython feature and a nice advantage. So, we've seen how to use Cython to operate with one foot at Python's high level of abstraction and the other at C's much lower level with surprisingly little pain involved in bridging that gap. We can use that knowledge to optimize bottlenecks in our programs or to access functionality that's only available when we operate close to the hardware. Earlier, we saw how to use ctypes to access already existing compiled code, making it relatively easy to call on useful features written in other languages. We've come to the end of this course. I hope you've learned a lot and have gained immense knowledge about Python. I loved putting this together for you. Keep learning.